Good morning, everyone.
Good morning.
Good morning, scholars.
Good morning.
Yeah, you guys are wide awake after a long day yesterday. You made it. You're back. And who's all presenting today? Almost all of you. Yeah, y'all look good. You're dressed up sharp. So welcome back. For those of you joining us for the first time today, I'm Caroline Schumacher. I work with the Astronaut Scholarship Foundation, and we're very excited to have everyone here for the day 2 of our Astronaut Scholar Technical Conference. They did an outstanding job yesterday, and I know you will do just as well today. I want to introduce our moderators for today. So we have Carol Fitzgerald-Tyler and we have Ashley Monahan. Ashley was a scholar and Carol's one of our trustees and works for Wipro in Global Change Management. I said that without it in front of me. Did I get that right? Okay, good. And so they'll be keeping us on time and making sure we stay on track. We should wrap around 1:30 today, and they're really good at making sure you get some stretch breaks and so forth. So they'll explain all the timing again to all of you scholars so that you have signals and stuff when to kind of wrap it up. Scholars, just a couple housekeeping items I'll remind you at the end as well. If you did not get headshots and you want headshots, they'll be in our ASF office in the Turkey Lake room. Do that after the conference. They won't be available till after the conference because our photographer will be running around in here. And then at 4:30, we have a mandatory walkthrough down in the ballroom for gala this evening. What time? 4:30. You guys are good. So I have said that you are the most prompt astronaut scholar class that we have had, that I have experienced. I am not allowed to give that official title till Saturday night, but so far you are the most prompt, and I've been pretty impressed with that, so good job. So without, I won't delay any longer. You're not here to listen to me. I'll turn it over to Carol. Thank you all.
Thank you, Carolyn. Good morning, scholars.
Good morning.
More. Good morning, scholars.
Good morning.
Awesome. I already had 3 shots of espresso, so I'm awake. Welcome back to day 2 of our technical conference. So excited. I got a chance to work with Sarah this morning on her presentation. Yesterday was amazing. Everybody who presented was incredible, very interesting, and I can't wait to see all of you again today. So about 5 minutes in each presentation. Ashley and I will be taking care of that. We have wonderful Michael in the front row. He will give you a signal when there's 1 minute left. So we'll call you up, we'll introduce you, and you will dazzle us with your brilliance. So it's such an honor to be here with you today. Thank you so much for putting forth all the effort to give great presentations to your friends, your colleagues, and so many other people who are very interested in your phenomenal work. So good morning, thank you, and we will get started with our first presenter, who is remote, and her name is Ariana McNamara from Purdue University. So please welcome Ariana.
Hello, I'm Meenakshi, and I'm going to be talking about a topological criterion for zero-sum sequences, which is work I did during my RU at Carnegie Mellon this summer. All right, so to start, I'm going to give you a theorem that Eros, Ginsburg, and Ziv proved that says that if you have 2 n minus 1 numbers, there's some subsequence of n of them which sums to a multiple of n. For example, if we say n was 3 and we look at the numbers 1, 3, 7, 5, and then 3, then we can find that 1, 3, and 5 sum to be 9, which is a multiple of 3. So this is a problem that isn't all that hard to prove using standard number theory techniques, but it's a foundational result in the field of zero-sum Ramsey theory. And Ramsey theory looks at the general problem of guaranteeing that you have a certain amount of structure present in large random systems. So the goal during this RU was to use topology to try and prove this theorem and to also get some generalizations. So to start out, what even is topology? Topology is the field of mathematics that looks at shapes. For example, we might study the surface of a sphere or a torus. And it might seem that topology is completely unrelated to these Ramsey theory problems, which is probably why it hasn't been used to study them before. But there's actually kind of a good reason to think that it might be useful, which is that if you zoom in on either of these shapes, they look essentially the same. For example, we live on the surface of a ball, but when we're sitting here flat on the Earth, it looks like the Earth is flat to us. And so we can't actually tell these two shapes apart from each other unless we look at the whole global structure of the shapes. And this is also true for our Ramsey theory problems, where we have to look at the entire 2n-1 numbers to be able to guarantee that we'll get that subsequence. So in topology, we use continuous maps to study these shapes. And so a continuous map, and so for example, if we look at a one-dimensional sphere, which is just a circle, and a zero-dimensional sphere, which is 2 points, then if we tried to make a continuous map between them, we'd have to map the entire circle to one of the 2 points. For example, this left one. And when we try and encode our problem in a topological space, we're going to have to make use of the symmetry of that space. So for example, with the spheres, we can look at the symmetry as mapping to antipodal points. So every point on the top gets mapped to the bottom, points on the left get mapped to the right, and vice versa. And if, like, for example, we were on the Earth, we would map all of you guys in Orlando to somewhere just off the coast of Australia. And what's nice about this symmetry is if you apply it twice, you get back to where you were. So you wouldn't have to swim for all that long before coming back to Orlando. But we can show that for any spheres, if you have a higher dimensional sphere going to a smaller dimensional sphere, there's no maps that really respect that symmetry. So for example, if we start with that top point in our circle, and then apply our symmetry to get to the bottom point, and then map over to our 2 points, we'll end up on the left. But if we first map to our 2 points from the top, we go to the left, but then we apply our symmetry, we go to the right point. So we get 2 different results. And we're going to be able to use that to prove our theorem by Erdos, Ginsburg, and Ziff. So to do that, we're going to first translate EGZ into a problem in hypergraphs. And we do this by taking our 2n-1 points and representing them as vertices. And then our hyperedges are going to be sets of n different points. So for example, we have each of these hyperedges has 3 points in it, and I've drawn 3 of the different hyperedges. And what we want to show is that there's one hyperedge that is going to have all its vertices summed to a multiple of n. So for example, this yellow one here. So using this, we can prove EGZ via creating a topological space that's kind of based on our hypergraph, and then using the n-fold symmetry of our hypergraph to show that we can't map to any spheres of some higher dimension. And so if we try and map to the simplicial complex that has all the vertices in 0 through n-1, and then we can show that we can't map to just the outside or the boundary of that simplicial complex, because that will look basically like a higher dimensional sphere. So we have to map to the center, which means there's going to be one edge that maps to all the vertices. And if we sum up all the vertices, we get a multiple of n. And so from that, we get Erdos-Ginsburg-Ziff's theorem. And what's really nice about this method is that we can generalize it by using other types of hypergraphs than just the complete one to get more general results about these zero-sum Ramsey theory problems. And there's a lot of open problems that are still left, so there's a lot to do. But yeah, thank you. Any questions?
Thank you, Ariana. We have a question for you.
Hi, Ariana. Great talk. Very easy to understand. I'm wondering if you could speak to the applications of Ramsey theory within or outside of mathematics?
Yeah, so Ramsey theory is a really broad area of mathematics and has a lot of open problems that are really difficult to solve. So within mathematics, there's a lot of applications to graph theory. This one's more on the number theory side. And that actually there's applications to Banach space theory, which is a more applied area of mathematics in some ways. And then I know that there's a lot of applications to like communication as well.
Okay, one more question.
Hello. I was wondering in the final slide when we talked about the sort of final stage was showing that there's no maps, that like trying to get that there's no maps between spheres of a lower dimension and a higher dimension, how that got you to the part of where that the subsequences would sum to n. Just making sure I see the connection.
Yeah. Okay, so our topological space we have that we create based on the hypergraph is kind of in a way like a higher dimensional sphere, or it relates to it in a lot of ways. And so if we try and map it to the surface of the simplex, for example, the picture that I have here on the right in that last slide, we can't map to just the boundary because that would be like mapping to a sphere that's slightly lower dimension. And so we can't do that and respect the symmetry. And so that means if we have a map that respects the symmetry, which we were able to construct one, then it has to map to the entire space, including the center of it. And that means one of the hyperedges has to map to all of the different vertices of that simplicial complex, the space that I have shown here. And if you add up all those different vertices together, you actually get a multiple of n always. And so that shows us, because of the way we constructed the map, that we have Ayers-Ginsburg Ziv.
Thank you very much. Ariana, thank you. We wish you were here with us in person, but very much appreciate your presentation. Thank you.
Thank you.
So our first in-person presenter today will be Cooper Jacobus from the University of California, Berkeley. Welcome, Jacob. I'm sorry, welcome, Cooper. More coffee, please.
Can you all hear me? All right. It's just the arrow keys, isn't it? Oh, the clicker. Yes. All right, so good morning. Thank you all for being awake so early. I know it's very early, so I'm going to do my very best to keep this non-technical. What you're looking at here is a simulation of the formation of structure in the universe. Since the Big Bang, the universe has been steadily expanding, and this competition between that expansion pressure and gravity creates this very fascinating web-like structure we often call the cosmic web. If you look closely, you'll see these bright emerging points are galaxies. You'll see they spiral with turbulent chaos, much like fluids here on Earth. You might not think of galaxies as being like fluids, but over billions of years, they're just gas and they behave the same. I don't know how long this video is. I'm not going to let it play out. If you zoom out even further, you can see this web-like structure much more clearly. In this picture, individual galaxies are barely a pixel big, and the space between them is filled with these thin structures we call filaments. So where is this cosmic web? You don't really see it in pictures like the Hubble Deep Field here, but if you look in the third dimension, you can see this structure emerge. So this is a picture, a map of galaxies nearby to our Milky Way, showing their distance from us, and you can see these structures very clearly. You can even see those filaments I mentioned before in the shadows of light from distant galaxies and distant quasars. So why do we care about this? Well, we can actually use this structure to learn a lot about the physics of our universe. Let's go next slide. By using those simulations and comparing them to real observational data, we can constrain important parameters about the growth of our entire universe. We don't know things like what is the overall curvature of space-time, or what is the average density of matter in the universe. It's very hard to just take a ruler between galaxies and measure those directly, but we can measure them indirectly by running tons and tons of these simulations and then comparing what we would see looking at those simulations to what we do see today. To do that accurately, though, we need to run something like 500,000 of those simulations. And each one of them consumes about as much power as a small town. So you can begin to see why this is a problem and why the funding agencies don't like us very much. But, okay, we'll talk about this first, how those simulations work. So it's pretty straightforward. We just program in all of the laws of physics that we think are relevant, things like gravity, things like fluid dynamics, and then we place that in a space-time that's expanding. Here's a very simple model. If the video will play. Hello. That's unfortunate. Oh well. What you would have seen was some little dots attracting towards one another, showing the formation of those structures. But I guess we'll skip that. The accuracy of these simulations depends on their resolution. So we can, of course, run very high-resolution versions of these simulations where every galaxy is resolved very well, or we can spend much, much less computational power running lower versions. So here's one that looks high resolution. Here's one that looks low resolution. These two are about a difference of 1,000 in computational cost. But the problem is we can't use this low-resolution one to do real science. The statistics that we would like to compare to reality just aren't very good. You can see all of the important regions are blurry and useless. But we can't spend 1,000 times more money doing the real ones, so somehow we have to resolve this problem. Now, here's that slide again. We want to translate between these two pictures using machine learning. That's what we're going to do. Hopefully, if we can employ some of the best techniques in modern machine learning, we'll be able to get back all of the high-resolution structure from this low-resolution picture. I don't think I have very much time, so I'm not going to talk very much about how the machine learning works, aside from saying, here's what our output looks like. You can see, I don't know if you can see from the back very well, but you can see all of the important structures come back. We can see all of these regions that start blurry get essentially unblurred by our machine learning model. And when we look at the statistics that we care about, we can see our machine learning model output is the purple, the input is the orange, and the target that we're trying to hit is the dashed line. So we can see that we get much, much closer, starting from something that's off by a factor of 50% and getting it down to something that's within a factor of 10% everywhere. Not perfect, but saving, again, a factor of 1,000 in computational cost. Another thing that we can do that is really, really exciting that no one has ever done before, to my knowledge, is estimate the uncertainty of our model's prediction. Our model is non-deterministic, meaning that if you run it over and over and over again, you'll get slightly different results. And if you look at the difference of those results, pixel by pixel, you can begin to see where is the model confident about the answer it's giving, and where is it uncertain. In the orange here, you see the absolute error of the model's prediction. Where is it getting the answer wrong? And on the left in purple, or on your right in purple, you can see where is the model unsure about its prediction. Where is it giving very, very different results when you run it over and over and over again? You can see spatially these correlate really, really well together. So well, in fact, that we can fit this power law to our data and show, even if these numbers are not exactly the same, we can actually make a pretty good guess about what the error is based on the uncertainty of our prediction. All right, I think I went a little fast, but thank you, guys.
Thank you, Cooper. We have time for one question for Cooper.
Great presentation. I know you ran out of time, but I was just curious what machine learning models you guys used.
So nowadays we're using diffusion. The results I've showed, those are all top secret until now, but the results I've shown you are just with UNets that we've modified to be non-deterministic by injecting some learned Gaussian noise in the upsampling path.
Thank you so much.
Thanks so much.
We'd like to now welcome Ruth Nichols from Florida Institute of Technology. Welcome, Ruth.
I'm going to go through these real quick. Okay. Okay,
Well
this is my
done.
slides. So my name is Ruth Nichols. I am a 2022 and 2023 Astronaut Scholar. My presentation is called On the Probability of Life Per Site. This is in collaboration with Dr. Langham at Florida Tech and Dr. Balbi at the University of Rome. So some of the most challenging and pressing questions are about, are we alone in the universe? Is there life elsewhere? And if there is, how can we find it and where is it? Understanding how life started on Earth can help us understand how life could start on other planets. So abiogenesis is a process through which life first originates from non-living materials. To go over some vocabulary, habitable means able to sustain life, like Earth is a habitable planet that we live on. This is in contrast to urable, which means able to start life. So being habitable does not necessarily mean urable, but we think the Earth has certain urable environments. So we sadly can't go back in time and see how life started. Abiogenesis is still very unknown to scientists, but what we do know is that we have a fossil record. and we can use fossil evidence to see what life might have looked like back then. We can do this with microfossils like this one, or with the stromatolites I showed on the title slide, which are some of the oldest living organisms on Earth. But another method is simulations, which is what we do in this project here using MATLAB. So to understand how life starts, we need to know what life needs to start. So this includes a solvent such as liquid water. We need bioessential elements such as carbon or hydrogen. We need energy of some sort, and then we need methods for concentrating elements and amplifying reactions. These are all essential for running the biochemical reactions that we need for life. All right, so there are a lot of questions about how did life start, when did life start, etc. What we're concerned with is where did life start? But also we want to quantify and model how many places did life start and how many times did life start on Earth. These are just some examples of potential sites where life could have started, including deep sea hydrothermal vents, I should probably use a pointer, deep sea hydrothermal vents, nuclear geysers, hot springs, or even impact craters and beaches. And these are chosen as potential sites because they have all the things that life needs that I mentioned in the previous slide. So I'm going to start breaking down some of the random variables we use in our model and simulations. So PL stands for the probability of life emerging at a given site. This will change depending on what site we're looking at. NU is the number of potential urable sites. This can depend on the size of the world we're looking at. Bigger worlds might have more environments. This can also depend on the time scale of urability. Maybe a given world is urable for part of its lifetime, but not its entire lifetime. And then finally, NL stands for the number of successful abiogenesis events. And this is essentially PL times NU. And what we're interested in is seeing how PL and NU relate to each other. All right, so again, we can't go back in time and see how life started ourselves, but we can imagine some very broad scenarios that might have happened. What if there were very few urable sites on early Earth? This is the pessimistic perspective, and abiogenesis is scarce. On the other hand, what if we had many urable sites? And this is the optimistic perspective, and abiogenesis is plentiful. The other option is somewhere in the middle at a moderate number of urable sites, and this is the uninformative perspective. So what we're doing is we're creating plots of the PDFs, or probability distribution functions, and CDFs, or cumulative distribution functions of PL for each of these different cases using different possible values of NU. So a PDF gives the probability of PL given a certain value, or the CDF is the value that is the probability that the CDF is the probability that the PL is at least some value. So I just want to say that this is still an ongoing project, and these results are kind of preliminary, but this is what our plots look like so far. So we see that we have the different perspectives up here. We have different colors for different possible values of NU. And we can see for a fixed PL, as we increase NU, the PDF increases. And then similarly for the CDF, sadly, the yellow line kind of overlaps with the purple line. But again, if we look at a fixed PL and we increase the NU, we see increased CDF. So ultimately, our results so far are saying, looking at the relationship between PL and NU, we see that PL depends on the prior probability, which is the perspective we're looking at, and also depends on NU. And the PDF increases as NU increases for a given PL. That's what I was showing with the plots. However, that does not mean that a higher NU means a higher PL. And that's because of the prior or the perspective that we're looking at. So ultimately, the number of urable sites can determine the probability of abiogenesis and the probability of life starting on a world. So as for next steps, we're trying to look at making lower bounds for PL and also refining our results. And finally, we want to look at other worlds besides Earth. So that's my presentation. Thank you all for listening. Thank you to Dr. Lingham, Dr. Balby, and the Astronaut Scholarship Foundation.
Thank you very much. Who has a question for Ruth?
Hi. So I'm assuming you're using Earth as your baseline calculation. When you're doing the number of urable sites, would that have changed significantly from now versus when life did first start on Earth? And are you taking that into account?
Gotcha. Yeah, that's a good question. So again, we're still working on our results, but we're looking at the number of urable sites on early Earth, so not current Earth. Yeah, good question.
One more question.
Hi, interesting talk. I was curious how you get the numbers for, like, say, Earth. Like, how do you validate your model? in a real world scenario?
Yeah. So I guess specifically some of the values we're using are in U, and we're still working on what values to use, but we try to determine that to be compatible with the Drake equation, which is a very famous equation in astrobiology, but also trying to think of what has likely been in the past Earth with looking at the number of sites that we know, looking at the fossil record. And then for our plots, we don't really use exact numbers, we just use powers of 10, looking at magnitudes, not specific values.
Thank you so much.
Thank you.
Next, let's welcome Olivia Bitcon from the University of Central Florida.
Hello everyone, my name is Olivia Bitcon and I'm here to talk to you all about the large-scale structure of the universe. But before we start, I want to paint a little picture for you. So imagine you're sitting outside at night looking up at the clear sky and you use your very extensive astronomy expertise to locate the Big Dipper. Now, while you're looking at it, what if you were to see all of those stars get closer together? Suddenly it's looking a little more like the Little Dipper. Or conversely, what if while you were looking at it, you saw those stars get further apart? That would be alarming, and it's not something you need to worry about, but it's essentially what I study. So I think Cooper gave a good background on large-scale structure, but I'll give you my take. It's formed by galaxies grouping together, and those groups of galaxies continuing to group together. So it allows us to see gravity itself, which is arguably the most important trait of large-scale structure, is that it's observable. We can see the interplay between gravity and the expansion of the universe through these observations. So what mostly forms it, as you can see in this little simulation here, you can see how it evolves in time. And the two factors that really play into it are gravity, pulling these structures together, and the expansion of the universe, really trying to pull them apart. So you might have noticed towards the end of this simulation, there's not as many changes, and that's because of the accelerated expansion of the universe. So you have this interplay between the strength of gravity and dark energy expanding the universe, but what if the universe doesn't continue to expand forever? A recent study suggests that the universe may not expand forever and actually turn around and begin contracting. And this would also explain a few other cosmological problems, which is why it's such a strong possibility to consider. So what I'm investigating is how large-scale structure would evolve in a universe that's contracting rather than expanding, and how far into the future would we need to be able to see to decipher between these two scenarios. So in order to do this, this is all very theoretical work, I did math. So if you're a math person, you'd like to see any of those equations, feel free to scan this handy-dandy QR code, but I won't scare everyone else off with equations. So lots of cosmological perturbation theory, some differential equations, and then in order to really see and interpret our results, a bit of coding. So here are those preliminary results. The most important takeaway, I would say, is that it will match your intuition. So without the competing forces of gravity and the expansion of the universe, now they're working together, the contraction working with gravity. So as you would expect, those structures form more quickly. Another important result to look at is the velocities of the elements of this large-scale structure, because galaxies actually do move quite fast in some scenarios. And that's another piece of data we can look at, but we haven't had much chance to interpret yet. As a next step, we're going to try to incorporate the statistical properties of large-scale structure into these plots so that we can get a more accurate timescale to determine how far into the future, whether that's geological, astronomical, cosmological scales of time, we would need to see in order to decipher between these two scenarios. Here are my references, and I would like to thank the Astronaut Scholarship Foundation for bringing us all out here, and also my advisor, Dr. Jim Cooney. So next time you guys look up at the night sky and you see those stars, think about all of the interplay of large-scale structures and all of the expansion of the universe, everything going on behind the scenes. Thank you. I'd like to take questions.
Thank you, Olivia. Who has a question on large-scale structures?
Hello. I was curious if, in addition to your presentation, you had any other signs or tells of ways to distinguish between the lambda CDM model and then a contracting model.
So there hasn't been much work on this yet, at least none that's been published. So to my knowledge, this will be the first thing in this area.
Congratulations.
Thank you. Yeah, it's all very new. So this is our best shot, but it probably won't be very observable to us as humans since it does take so much time for those effects to compound.
Another question for Olivia. Anybody? All right. Well, it was fascinating, and we had a chance to work on the presentation, and you painted a beautiful picture of contracting stars.
Thank you.
Thank you, Olivia.
Thank you all.
Next, we'd like to welcome Harrison Blake from Ohio State University.
Is the mic working? I'm very short, so I need a booster seat. Okay, so clicker, please work, fingers crossed. No. There we go. All right, hello everyone. I hope all your coffees are kicking in. My name is Harrison Blake. I'm a rising senior at The Ohio State University studying physics and astronomy. And today, my talk is as much a research presentation as it is a sales pitch. In that I'm trying to sell to all of you that we should put our best and brightest minds together, and a lot of money, to create the most ambitious idea for a telescope ever devised, which is a fully operational gravitational wave detector on the moon. So for those of you who don't know what a gravitational wave is, it is a ripple in the fabric of space-time, like a ripple of water in an ocean or a lake, caused by the most violent and energetic events in our universe. What I have up here is an example of two black holes that are slowly coming together over years, months, days, hours, and seconds, and merging, producing a very massive gravitational wave that we can hear back on Earth. We call these BBHs for short. Gravitational waves come in many different kinds of flavors or frequencies, and depending on how we construct our telescopes to hear them, we can hear different parts of the spectrum. Earth-based detectors are very good at hearing waves in the kilohertz frequency, and space-based detectors, some of them launching in the 2030s and 40s, will be able to hear waves in the millihertz spectrum. However, these two regions of the frequency spectrum leave a very important part of it out, which is the decihertz frequency. The place between these two frequency ranges holds an immense amount of information that we are simply not getting with any of our current detector ideas. So now, I propose we use the moon. So the Lunar Gravitational Wave Antenna is a proposed detector that will be deployed on a future moon mission like Artemis, where we go around, deploy several seismic stations that are very well attuned to how the moon shakes and vibrates when a gravitational wave passes through it. Of course, this seems very like a simple idea. Just go up there, put a bunch of seismometers up there, and leave. But the question is, how effective will this even be? Firstly, I want to talk about why we even chose the moon in the first place. Why don't we just slash the cost and just do this on Earth? That's the multi-million-dollar question here. So firstly, the reason why we chose the moon is that it has no atmosphere and no ocean to get in the way to produce noise that might mess up our data. The moon is essentially geologically dead, so it'll actually detect gravitational waves instead of earthquakes and other things getting in the way. Millions and millions of dollars are currently spent on cryogenics for detectors on the Earth, whereas if we just put our detectors in polar craters that are blocked from the sun and are cold all the time, we don't have to spend a dime. The most amazing part of this, and the reason why I really want to talk at this conference, is that this has already been attempted before by astronauts. On the Apollo 17 mission, the lunar surface gravimeter was sent to the moon. However, a technical failure rendered all the data useless. And now that people are looking to go back to the moon, we're looking to put a detector back up there as well. My research studied the binary black holes, or BBHs for short, I was talking about earlier, and with our current fleet of gravitational wave detectors on Earth, we can only hear these events in the kilohertz frequency, which is basically right when they collide. We want to be able to hear these waves when they're orbiting years and months and hours in advance. This is really the ball game, the fighting arena of the space-based detectors that are in the millihertz frequency. However, we still need to bridge this gap, which I propose we use the moon. So this is an example graph of what I would typically do this summer. This is actually a model of the very first gravitational wave ever detected, as it would have been detected by the future fleet of gravitational wave detectors, including the Einstein telescope, a ground-based detector, the Laser Interferometer Space Antenna, which is obviously a future space detector, as well as the moon detector. The way we measure how effective a detection is called signal-to-noise ratio, which in layman's terms is the area between the signal curve and the noise curve. The more area you have between these, the better our detection. My research involved simulating a bunch of these binary black hole events and modeling them on graphs to calculate their signal-to-noise ratios using these two very cool codes. I love this logo so much. And this is a typical graph that we would get. This is a sample of about 1,000 binary black holes. And something that actually surprised us as researchers is that the lunar gravitational wave antenna pulls a lot of weight. A lot of people in the literature were talking about LISA doing a lot of this work, but apparently when you go to a full sample size of 75,000 waves, of course the ET is very effective in detecting these, the LISA only detects 2, whereas the lunar gravitational wave antenna detects on the order of 100. An immense amount of science can be done, far more science can be done with the lunar gravitational wave antenna than we could ever get with LISA. So now, looking at this graph and the other one, it's not a question of if we should put this detector on the moon, it's why are we not? So the final conclusion that I have for all of you is that an effective way to model how effective detectors are is that we simulated waves and discovered that the model moon detector actually is way more effective than we thought and even better than current models for space-based detectors, which means that the lunar gravitational wave antenna is a vital piece of the puzzle of future astronomy. Here are all the people I want to thank. Do I have time to go through individually? Yeah. All right. So I want to thank my research mentors who taught me a lot of skills at Ohio State, Chris Harada and Makana Silva, Wayne Schlingman and David Zak, who are my academic advisors and some of the best people in the world. The people at the University of Florida, Paul Folda, Peter Wass, Catherine McGill, and Nathaniel Strauss, who got me to and from Europe in one piece. My research advisors and friends at Bicocca, Davide Garosa, Michele Mancarella, Giulia Fumagalli, Alberto Cesana, and of course, all the people who are not up here, who are the amazing friends I made along the way, which now include all of you. Sorry. Woo. Thank you.
Wow. Thank you, Harrison. Who's got a question?
Oh, there's a lot. Okay, wow.
So would the scope of the information you would be able to receive, would it be limited only to binary black holes, or would it be more expansive than that and more useful than that?
Oh my gosh, you led into like one of the things I also want to talk about. Thank you. The future avenues of this work, there's many other things that detectors can detect. For example, black holes are the product of when massive stars die, and there's another product with slightly less massive stars called neutron stars. When the two of them get into an orbit and collide, they produce a big gravitational wave, as well as most of the elements that make up us. So like your carbon, your iron, your heavy metals, all of that. Also, something that's very special about the decihertz frequency is that it will be able to detect what are called intermediate mass black hole collisions. So you have supermassive black holes, which are the centers of galaxies, as well as the stellar mass black holes I talked about. However, we have no idea how we got from these tiny little black holes to things that literally center around galaxies. And we're hoping to find some of those intermediate mass black holes with the lunar gravitational wave antenna.
One more question.
What about primordial black holes and the cosmic gravitational wave background?
Ooh, fantastic question. I chose not to talk about nanograv. I'm sorry, Olivia. It's basically in the nanohertz flavor of gravitational wave. We can hear a general background of gravitational waves produced by the collision of supermassive black holes. That's a very important part of the frequency. If there are proposals for decihertz detectors in like the 2060s and 2070s that are proposing on digging into some of that in the decihertz frequency, although as you can see, the noise curves are way too high to do that right now, which is kind of sad. But primordial black holes, admittedly, I don't know much about how we would detect them with these, although I assume that if you had like electromagnetic effects, like Hawking radiation, you could maybe see that in a telescope.
All right, mille grazie, Harrison.
Thank you so much.
All right, next, let's welcome Luis Santori from the University of Central Florida. Welcome, Luis.
Hello, everyone. I'm going to be talking about photometric analysis of pure anthracite exposures. Now, for little geology background, the most common minerals on the on the moon are pyroxene, olivine, and plagioclase. I'm particularly interested in a rock known as anthracite, specifically pure anthracite, which is 98% or more. Plagioclase, which would be at the top of that tertiary diagram. Now, it's hypothesized that Moon's early beginnings, it was mostly molten. As it cooled, minerals such as olivine and pyroxene began to crystallize. They were denser than the magma, floated to the bottom, and created the lunar mantle. And then plagioclase crystallized, floated to the top, forming what is now known as the anorthositic crust. Now, that doesn't look great, but here, this image was derived using M-cube spectral data, but in red, you have plagioclase. In blue and green, you have olivine and pyroxene. For my research, I'm mostly interested at the relationship between photometric analysis at a high spatial resolution and located pure anthracite exposures using spectral data, specifically diviner data. Now, a little background on the instrument. I'm using the Lunar Reconnaissance Orbiter narrow angle camera. There's two narrow angle cameras on board LRO. They're identical, and they take images at a resolution of 0.2 to 2 meters per pixel. Now, in order to do the analysis, I need to create a digital terrain model, which you can just think about as being an image in which each pixel holds elevation values of the corresponding terrain. Now, in order to create the digital terrain model, you need stereo image pairs, which are just images of the same area at different angles. And those, at different angles, that creates an effect known as parallax. You can calculate it to then derive the elevation of that region. In order to create them, we use ISIS and NASA's AIM stereo pipeline. In order to improve the overall accuracy, we use the Lunar Orbiter laser altimeter, and we downsample the data to 5 meters per pixel in order to decrease the noise in the final product. Now, I'm using the Hapke photometric model. So we use the DTM. Why does that keep happening? We use the DTM to correct the LROC NAC images to a common view in geometry and reflectance that reduces the effects that local topography is going to have on the derived parameters. And then we use a nonlinear optimization algorithm to minimize the simplified version of the Hapke equation, which makes assumptions on grain size and space weather and maturity. Now, the parameter I'm mostly interested in is single scattering albedo, which is the ratio of scattering efficiency and total extinction efficiency. Single scattering albedo depends primarily on composition, and from previous works, we know that a single scattering albedo greater than or equal to 0.6 is likely areas of pure anthracite. Here is the derived single scattering albedo map. On black, you have the region of interest, which is pure anthracite, and the cooler colors are lower single scattering albedo, and warmer colors have a higher single scattering albedo. Now, for analysis, I'm looking at the relationship between single scattering albedo and iron content, optical maturity, rock abundance, and slope. I'll only be talking about iron content and optical maturity. Now, for iron content, there seems to be a negative correlation between iron content and single scattering albedo. As iron content increases, single scattering albedo seems to decrease. I've looked at, 10 different craters, and we have a correlation coefficient of -0.66. And then for optical maturity, there seems to be a positive correlation with more immature craters having a higher signal scattering albedo, and we have a correlation coefficient of 0.91. That's all. I'd like to thank Dr. Carrie Donaldson-Hanna, my supervisor and mentor, Melissa Martinot for mentoring me and also helping with the creation of the ROIs, Ryan Walkings with helping creating the pipeline, and Madeline Meinhain for helping create more accurate digital terrain models.
Thank you, Luis. Questions? Did everybody fall asleep? No? All right. No questions. You did fabulous. Thank you, Luis.
Well,
I think we have
Oh,
one question.
sorry. See, there is a question.
Thanks, Louis. I'm curious how you chose the specific craters that you wanted to look at.
So the craters were picked from Dr. Donaldson's previous works on kind of surveying the whole lunar surface and looking at where you find pure inorthosite exposures using diviner reflectance data. But for the most part, they're all in either central peaks or lunar basins.
Awesome, thank you.
Yeah, no problem.
One more question.
What is the value of knowing the locations where there's the pure anorthositic sites on the moon?
So it's not a matter of like kind of location. That's the only place where we can find them, since there's no atmosphere on the moon, so most of the moon's surface is covered in regolith. So you can only get kind of pure anorthosite exposures on central peaks and basins. But the main motivation is learning on how the moon formed and how well the plagioclase segregated from all the other minerals.
All right. Thank you so much. Next, we would like to welcome Vikas Patel from Embry-Riddle Aeronautical University. Welcome, Vikas.
All right, thank you, everyone. So I'll be talking a little bit about battery testing for space applications. So at the Space Technologies Lab, we were given the opportunity to develop a camera system to record the first commercial spacewalk aboard Polaris Dawn. And for such a unique mission, we needed to develop a novel test plan for our system. And so we used 18650 cells, which is a common form factor of lithium-ion batteries. And so our test plan needed to address two main concerns. First of all, safety. We had to make sure the batteries operated at a safe operating temperature and didn't undergo what's called thermal runaway. Also, we had to make sure that the batteries lasted for the full duration of the mission, despite space's harsh conditions. It's known that under cold environments and vacuum, lithium-ion has some power losses and some performance degradations. So we had to make sure that we could last our full mission and meet the requirements. And so there on the bottom right, you can kind of get an understanding of what our camera system looks like. And for those of you who are interested, we needed to supply 28 watts of power. So we selected 3,300 milliamp hour batteries in a 3S2P configuration. And yes, we know it looks like Wally. And so the tests we ended up with were comprising of making sure we met our safety requirements and our performance requirements as well. So we conducted a maximum discharge test where we did a single cell discharge at 10 amps. And so that kind of is an order of magnitude higher of what we expect to see in flight, and to kind of make sure that we have enough ample room and are still within safety boundaries. In addition, we know that vibration can cause internal shorts and other defects in batteries, resulting in unsafe hardware. So we had to make sure that we could both withstand the launch environment as well as operate safely right after that. Also, we did a full system vacuum test. So as you can imagine, in a vacuum, we don't have air to provide convection cooling. And so we had to make sure that even despite that lack of cooling, we could operate at safe operating temperatures with the internal heat generation that is going on with the batteries. And lastly, we did thermally controlled discharge testing where we held the batteries at cold temperatures to make sure that we could last the full duration of the mission and still meet all of our requirements. And so that last one is what I'm going to delve into a little bit today. So with lithium-ion batteries, it's known that cooling them down dramatically increases their internal resistance, which is shown on the left graph in a couple of ways. So first of all, with all batteries, whenever you have power draw, you have this thing called voltage sag, which is a function of internal resistance and current draw. And so there on the left, you can see that as soon as the power draw initiates, there's a dramatic drop in voltage, and that gets worse with the temperature that we're operating at. In addition, with the higher internal resistances, we have much more heat losses and heat inefficiencies, and so we end up getting less of a discharge capacity throughout our mission. However, that internal heat generation isn't necessarily a bad thing. That heat generation actually ends up warming up the batteries as well, and so that kind of results in a self-regulating heat effect. And so on the right, you can kind of see, those of you in the back might not be able to see, but there's a sawtooth pattern, especially evident on the top graph here. And that sawtooth pattern is a result of the internal heat generation and the cooling that was required to maintain the test temperature. And so that sawtooth pattern is much more fine and much more dense at the colder temperatures, which kind of goes to show you the much higher heat generation that's conducted at that temperature and how much more active and aggressive cooling that was required to maintain our test temperature. And so from these results, we were able to determine that we were indeed able to last for the full duration of the mission, even at negative 20 degrees Celsius. And that internal heat generation and self-regulation also adds an additional safety margin on top of that to make sure that we last the full duration mission, even if something were to go wrong. And so with that, I want to give a special shout out to Dr. Troy Henderson, our faculty advisor, and the other members of the Space Technology Lab who have given me so much in terms of knowledge and power. And lastly, I want to thank the Astronaut Scholarship Foundation for the opportunity to be here. And so as I draw this to a close, I just wanted to bring up something that kept coming up as we conducted our testing, and something that some of the astronauts have also mentioned, and that is that as we sit here today and continue with our careers, we're going to innovate in science and technology, and we're going to continue to push boundaries. And so it's really important that we keep human safety as our #1 priority. And so with that, thank you for your time, and I'll open it up to questions.
Thank you very much. Who has a question?
If you found that the batteries wouldn't have lasted the whole mission, what design changes might you have introduced to resolve that?
We would have had to redesign our power system, so either go with a different capacity battery or change the configuration. So the 3S2P is basically 3 battery packs in series and 2 in parallel, so essentially 6 battery packs. And so we would have had to put more in parallel to increase our total capacity.
One more question.
Yes.
I'm curious about how much a battery system like this costs.
So the good thing about F18650s is that they're a common form factor. And so the main reason we had to develop such a novel test plan was because most of the testing that was conducted is by NASA and all these other companies that have much more ability to conduct full-scale testing. And so for us, it was really important that we developed a test plan for these 18650s at a much more approachable level. And so you can get various 18650s for about, I think, $60 each. And so that's much more achievable for a student payload, for example.
Awesome. Thank you.
Thank you so much, Vikas.
Awesome. Thanks so much.
Next, we'd like to welcome Winter Jones from Spelman College. Welcome, Winter.
Good morning, everyone. My name is Winter Jones. I'm going into my 3rd year at the illustrious Spelman College, and I'm studying mathematics and aerospace engineering. Now, at Spelman, our motto is a choice to change the world. So I entitled my project, A Choice to Build a Rocket Engine, Optimizing Paraffin Fuel Grains. Now take a moment to imagine with me. What if we could fuel rockets using candle wax? Now, you may think that this is impossible, right? We light candles all the time in our homes, and there's no big explosion. However, it is quite possible because of paraffin. Paraffin's chemical formula is CnH2n plus 2, where N is the average value between 20 and 30. Paraffin is a hydrocarbon, meaning that it's completely made up of hydrogen and carbon atoms. Now, hydrocarbon atoms are very important. Hydrocarbon fuels are, and you notice that we have kerosene, which is a type of hydrocarbon, which is also fuels rockets and your vehicles and things of that nature. There's also petroleum jelly, which has a lot of benefits for the skin, and paraffin wax. Now, 95% of our candles worldwide are made up entirely of paraffin wax. Both paraffin wax and kerosene can be used as rocket fuel, but they have their differences, and paraffin wax has its drawbacks. One of the major drawbacks is that its volume is dependent on its temperature. So, on a large scale, it causes a lot of cracking within the fuel grain. A fuel grain simply describes the shape that a fuel takes inside of a rocket engine. So if you've ever lit in a candle and you may have not let it burn all the way out to the edges, you may notice that there's this tunneling effect. Well, in a candle, that's fine, right? You're gonna toss it or keep using it and nothing's gonna happen. However, in a rocket engine, this is actually detrimental because anything that is not cohesive can cause an unexpected explosion. And we know that you want explosions to be expected. You wanna prepare for them, right? So how do we circumvent these drawbacks? One of the things that I did was design and build a fuel grain casting system and technique, where I took these acrylic tubes and I extended the tube using cardstock. I would then take a teaspoon of paraffin wax, put it inside the tube, and fill it all the way up, including the cardstock. After that, I let it cool for a moment, remove the cardstock, and cut off the excess wax. This decompresses the different contractions and things that we see happening within the wax as it cools. The next step was to actually build a model hybrid rocket engine. Now, I really want to emphasize that this is a model because I know you see that there's a wooden cap here, and in reality, you would not want wood anywhere near a rocket engine. So here we have the wooden cap. There's also plumber's tape. Plumber's tape is not very heat resistant, so that will also need to change. In order for a flame to remain lit, you need oxygen. However, in space, there is none, so you must bring your own oxidizer. So we also have the oxidizer entry point, the combustion chamber, which is where the fiery reaction would take place, and the nozzle is where the fire would escape. I would like to thank everybody on this slide for supporting me. It is not easy or really anticipated for an undergraduate to be a principal investigator of a project funded by the Department of Defense. So I want to thank everybody on this slide for supporting me through the trials and tribulations, and of course, the Astronaut Scholarship Foundation for allowing me to present today. Thank you, guys. Thank you. Here are my references. And a brief recap, you learned how candle wax can be used as rocket fuel, the major drawbacks of the fuel, and how we can circumvent these problems. I'll now be taking any questions.
Wow, thank you, Winter.
Hi, great talk. I was just wondering how you got into this entire project, or were you like approached with it, or was this something that you have been wanting to study?
Thank you. That is a beautiful question. So this project actually derived from an elementary school science fair project. I've been experimenting with paraffin wax since I was in 3rd grade. I first started studying the refractive properties of the candle, and then in middle school, I learned that the wax could be used as rocket fuel, and I have been experimenting with it ever since.
Great. Next question.
Hi, this is a really great project. It was really cool. Can you say anything about the differences in like the emissions with like paraffin wax versus traditional fuels?
Yes, so the World Health Organization actually discourages kerosene to be burned for indoor use because it actually has a lot of respiratory problems where people get cancer and things of that nature. Paraffin wax is actually non-toxic. It's actually edible. They use it in gourmet chocolate to like help it make it shiny and everything like that. Now there are some, like nothing is gonna have a 100% clean burn, but compared to everything else, paraffin wax is the best thing in the market.
Great, thank you so much. And the hair on fire, it looked like me on Thursday morning on a call, so thank you for that. Thank you, Winter. Very
Thank you,
good.
guys.
So we want to welcome next Lucy Waite from the Virginia Polytechnic Institute and State University. Welcome, Lucy.
All right. Good morning, everyone. My name is Lucy Waite. I'm a senior at Virginia Tech studying aerospace engineering. I'm going to be talking about a project where we're trying to identify the high temperature materials of additively manufactured Inconel 718. My specific focus was trying to develop a digital stress strain analysis tool to find these properties. So a little bit of background, Inconel 718, or as I'll be calling just Inconel throughout this presentation, is a material commonly used in things of aerospace applications where they'll be experiencing really high temperatures, like rocket engines or jet engines and things like that. One of the things that we are trying to find out is whether or not additive manufacturing would be a viable method and how much the defects within the additive manufacturing process will affect these material properties. My specific focus, since this project is really in the beginning stages, was to try and work on a digital stress strain analysis tool to find the most basic material properties just to start. These would include things like the Young's modulus, the yield stress, and the elongation at fracture. There's already a lot of tools that exist that can find these properties at regular temperatures. These would be like strain gauges or digital image correlation tools, but very few of these function at really high temperatures due to your standard strain gauges melting or digital image correlation tools being affected by heat haze and things like that. So, and there is one existing strain gauge on the market for high temperatures, but the issue with that is that it's one-time use only. You have to weld it to the part, and once that's used, you can't use it again on any other part. So my goal is to try and utilize some DIC or digital image correlation techniques and make a reusable method. So just to give some background on how I did this experiment, I was using an Instron East 3000 fatigue testing machine and using the MATLAB computer vision toolbox, which can digitally track black or dark points on a sample. And since I was really just testing the framework and the testing tool, not necessarily Inconel just yet, I was using Steel for my tests to start. So the way that my program worked was I took a tensile test of this steel sample. I took 300 images over a 300-second tensile test. The material was tested to failure, and the MATLAB toolbox used the computer vision capabilities to track these dark marks on the object over time in order to find the strain of the object over time. And for some sense of scale, this sample was about 0.6 inches. So the resulting data was looking really great. It produced a great stress strain curve at which was able to help me find some of the elongation and fracture properties that I was looking for. And to zoom in a little bit on the elastic region, you do have the characteristic elastic region, which is below about 0.2% strain. So you have that section right at the beginning that is a straight line, and then it kind of tapers off right here. That is the transition over into the plastic region. So the stress strain curve did come out really great. But I did find in some post-processing that the tool was really effective at strains of about 0.8% or higher, but wasn't really effective for the elastic region that I was wanting to also analyze. So looking at properties like the Young's modulus and the yield strength, those weren't quite producing accurate results to the steel that I was testing. And I'm hypothesizing that this is since the elastic region, or around 0.2% strain, really only looked at anywhere from 3 to 6 pixels in displacement. So going back to the picture over here, this delta L would have only really been 3 pixels long in that elastic region, which really wasn't enough to give accurate values for the Young's modulus. So one potential thing that I'm thinking of doing to mitigate this and working on this in upcoming semesters would be to get potentially a higher resolution camera or perhaps tracking a different pattern on the sample. So instead of tracking lines, maybe tracking a speckle pattern on the sample as well. So I discussed this a little bit with the higher resolution camera. We're not, at this time, I'm not quite sure what approach to take with that. If we get an 8K camera, this only really increases the resolution by 2. So I'm not sure if that will be enough to mitigate the issue of the displacement being so small. And then even after that, we do still have some room to develop the techniques needed to test at high temperatures as well, because once you get into high temperatures, you come up with additional issues to the digital process as well. So when you're testing this sample, we want to ideally be testing it at 1,000 degrees Kelvin to find the high temperature material properties. And one of the biggest issues when testing at that temperature would be something called black body radiation. So this would be like when you heat up your stove, it glows red. That would cause issues to the black pattern that we have on the sample and make it harder for the digital tool to track it. So one way that we're thinking of mitigating that is by illuminating the sample with a blue light or having a blue lens filter on our camera for the tracking process. But that's also something that I plan on working on in upcoming semesters. So some acknowledgements. I want to thank my research advisors in the Material for High Temperature and Corrosive Environments Lab, Dr. Yao Fu and Dr. Jia Song. And I wanted to thank the VSGC, or the Virginia Space Grant Consortium, and the ASF for funding my education and my research. So thank you.
Thank you, Lucy. Question for Lucy.
Hi, Lucy. Great presentation. Very important work. I have one question. While you're looking at designing this method, have you thought about different atmospheric conditions, such as high sulfur environments or even a vacuum? Because that changes mimics the operational environment and changes how the material behaves.
Mm-hmm. I haven't looked into a high, like a sulfur atmospheric environment, but I have considered vacuum environments. The biggest issue with that is trying to get all of our instrumentation in for like heating. Right now, our plan for heating was to use an induction coil, which I'm not sure how we would get everything hooked up to that, and then working with the Instron machine as well, and put it through the vacuum environment. But that's something I can definitely look into. So.
One more question for Lucy.
Hi, thank you for your presentation. I had a question. So I know most stress strain curves, you don't really use a visual method. It's more just like the machine pulling on the dog bone. Does the fact that you can put like multiple points and look in your image at like more than just 2 points add any additional information you can get from this testing method?
If I were to have more than the 2 points, then I could potentially look at the variation of strain along the piece. I'm not sure if that would necessarily change the full picture of like what the overall strain of the material is, but we could definitely maybe look into more localized variations in that stress and strain. So.
Thank you so much, Lucy.
Thank you.
Well, so far this morning, we've been scared by contracting galaxies, but we have batteries and we know how to use candles for rocket fuel, among other things. So thank you all. Because you are so wonderfully on time, you get a whole 5 minutes to stretch. Yay. Thank you, everybody. We'll be back in 5 minutes, please. All right, it's been 5 minutes. Please take your seats. Welcome back to the next portion of our technical conference. Please take your seats. You guys are so good. Welcome back. Welcome back. All right. Well, thank you for being prompt. Our next set of presenters are getting ready to go on stage. So welcome again back to the technical conference, and let's start with our next presenter from the United States Air Force Academy. Yay, Luca Valenti. Welcome, Luca. Buongiorno, Luca.
Hi, I'm a cadet second class, and for those of you who don't know, that means I'm a junior in college. That's pretty much it. I'm going to be talking about something that I find very fascinating, and it's flight dynamics inspired by birds. So we've come a long way in human flight in our atmosphere, let's be clear. But there are a couple things, actually more than a couple of things, that birds do that we still can't really manufacture or put into the capabilities of our aircraft. Some of these are energy management capabilities, how they manage their energy state and how they land basically on a perching point without using a runway, even though they kind of have a fixed wing aspect when they do that. Another aspect is maneuverability. So birds are able to maneuver in a forest, in very tight spaces, in ways that not even our drone racing teams can yet do. And then the third aspect is the load capabilities. Some birds are able to lift as much as 100% of their own weight, and they're including their own fuel. So I'd like to focus with my research, and this is a research proposal, I'd like to focus on the third aspect. What effects does that have on their flight dynamics, being able to lift 100% of their weight? And how can we incorporate and use research to inform the manufacturing of our own aircraft and of our own load placement to enhance our load capabilities? Let me see if the clicker works. Other way? There you go. Okay, so if you don't believe me about the 100% weight load, let's look at this example. Look at this bird. This bird is an osprey, and it's about 3 pounds, and it's carrying a fish that is also about 3 pounds. So there's a couple of aspects that you might notice, some of our aero engineers in the room might notice. So birds have 1/3 of their weight in their legs. The legs of this bird are in the back of the center of the structure, and as well as the fish, which is already 100% of its weight. So we're willing to bet that the center of gravity of the whole structure is behind the center of lift. Now, center of lift happens at the quarter chord, usually for fixed-wing aircraft, so that's our assumption there. And for the air engineers in the room, you might know that that causes a pitch-up moment, and that's unstable. So how is this bird able to counteract this unstable configuration and create such a flight that is pretty seamless? Especially, I don't know if you noticed, the fish at some point starts to wiggle, and the bird doesn't even care. So what control surfaces is the bird using, and what other effects are there? For example, one might think the tail, if you noticed, I don't know if I can replay this, probably not. I don't want to mess up. So the bird had its tail all the way deflected down, which creates a counter pitching down moment, which could counteract this unstable configuration. But also, there might be pendulum stabilization tendencies, like the glider, hanging glider effects, because if the prey is behind the CG, it might create enough drag to create a pitch down moment. And so there might be 1 or 2 of these effects that are working together to make it a stable flight. Let's look at another example, which I found even more fascinating because it's a golden eagle taking off with its weight. So the golden eagle is about 7 to 15 pounds, and it's carrying a red fox, at first only with 1 leg. And it's taking off, which is even harder than just gliding. So the cool thing is the load distribution is not even symmetric at first. So the bird is flying, carrying the eagle with just 1 leg, and it's still able to manage that. So we want to model a little bit of that. And how are we going to do that? Well, we want to answer the questions: what are the control surfaces that they're using? If there's anything that we can do with our planes similar to that, and what are the effects on dynamic stability? Our model is going to be pretty simple. It's going to start from analytical assumptions about the CG, the quarter chords, some trig, and then I don't know why you can't see it, but we'll use the inertial properties of 20 species that were gathered by Dr. Christina Harvey, which is one of our collaborators. And she actually published a very interesting paper on how birds can transition between stable and unstable configurations, which are useful for different purposes. A stable configuration is good for long-range flying, but unstable is good for maneuvering flight. So if we could get some of that in our aircraft, that we can make them more versatile. So why is this important? Well, apart from that part of the aircraft, think about the fires that are happening today in Hawaii. What if we could carry more load in a safe way to extinguish those fires sooner? What about drones and delivery drones? So right now they're using hovering technology, right? And hovering is somewhat of an inefficient way of flying because thrust needs to be greater than the weight. So if we want to increase the autonomy and the range of these drones, given that these drones are powered by batteries, and so that they will need to deliver a lot of packages, then this research could help us do that. Of course, there's some other things that we need to keep in mind. For example, we'll have to model the perching aspect in order for the drone not just to carry 100% of its load, but to also land it safely without breaking your Amazon package, for example. So this is my proposal. I don't know what happened with the frame there, but I'd like to thank our collaborators, Dr. Samuel Stanton from the Air Force Academy and Dr. Christina Harvey from UC Davis. And I'd like to thank the Air Force Academy for allowing me to serve our nation and to do awesome research while doing that. And I'd like to thank the Astronaut Scholarship Foundation for having me here.
Thank you so much, Luca. First question.
Hey, I was going to ask, what are the main avenues of areas that you're going to explore? Is it like the bird changing its angle of incidence or airfoil? What do you plan on investigating first?
So the first thing that we plan on investigating is the length of the tail compared to the length of the rest of the body. And then how are we going to compare that with a fixed wing that is not a delta wing, so where the wing are not the full, don't cover the full fuselage, and how are we going to compare the two? Because with a bird, it's more kind of like a delta wing, and there's a big component of the bird's lift surface that is composed by the tail. So we're going to investigate how much, well, doing a couple plots, how, once we have our model, how changing where the tail starts is going to affect the dynamics.
Next question.
Yes.
So one thing that makes birds so efficient is that they're able to vary their wingtips, and so that they lose a lot less lift from that. There's less pressure coming from the bottom of their wing to the top. So how do you think that we could model that in aircraft or in drones present day?
So that's actually a very interesting question. It's opening a whole new field of wing morphology, which is a field of research that's active and pretty new. And we're trying to model more and more of that by increasing the degrees of freedom in the wing, because that's one of the main issues. So I see in the future, after figuring out this load issue, then perhaps I could do some more research on the different degrees of freedom, the shoulder, the wrist, the elbow, and looking at how that could enhance our capabilities. And if there's two things. If there's a manufacturing issue, because it's difficult to, the more degrees of freedom, the more complex the machine is, the less reliable it could be. And then the second aspect, is there a scalability issue? Because when we're talking about drones, yes, perhaps they have the same size as birds, but when we're talking about a big plane like a C-5, there could be some scalability issues that are beyond what we can do. So we'll see.
Thank you, Luca, inspired by nature, and thank you for your service.
Thank you so much.
Let's welcome our next presenter, Lucia Torres from the University of Oklahoma. Welcome.
Hello, everybody. Can you hear me? Cool. Hello everybody, my name is Lucia Torres, and today I'll be talking to you about GotJam, a project I developed and worked on over the summer at SIZL, the Stanford Intelligent Systems Laboratory. And this is an anti-jamming technique for radar using POMDPs. The main motivation for this project is the bandwidth crisis, which is the overwhelming demand for data transmission channels and the lack of them. So listening to the radio, connecting to Wi-Fi, using Bluetooth, all these things take up bandwidth. And there's an overwhelming amount of technologies that take up bandwidth and such a limited amount of it. And this causes some negative effects, such as slower browsing, more buffering, and just an overall lower quality experience. But if we could efficiently share bandwidth, we could mitigate the strain that we have on the limited bandwidth we do have so that these technologies can continue functioning properly. And that's exactly what I did with my project. I used radar and a common technique called frequency hopping to mitigate radar interference and thus efficiently share bandwidth with other technologies. Now, radar is a technology that emits a wave, and the returns that we get gives us information about its environment. A jammer for this project is any interference that contaminates and deceives the radar. In the terms of the bandwidth crisis, this would be any other technology that's trying to access the same bandwidth as the radar. And this doesn't only cause the radar to not function properly, it also causes that technology to not function like it's supposed to. So now your Netflix is buffering at the most crucial moment, and that thing you're searching on the internet is just never loading. And so I formulated my problem as a POMDP, which is a partially observable Markov decision process. And this is a mathematical model of a sequential decision-making problem where there's some sort of uncertainty. And the uncertainty for the radar lies in that it does not know what the other technologies are around it or what other technologies are trying to access the bandwidth that it is at. But it can observe when it is being interfered with, when there's some sort of technology interfering with the radar. When we have this POMDP, we can generate an optimal policy. And this is a strategy that tells us the best action to take, the best frequency hopping to do to mitigate this interference and efficiently share bandwidth. To set up my problem, I started with the state space, which is the environment we create for the radar, the world it lives in. The action space is the actions that it can take, so the frequency hopping it does within this world we have created for it. The observation space and function is how we relate the observance of being interfered with back to the state that the radar is in within this world. The reward function is how we quantify how well the radar is mitigating interference and thus how well it is sharing bandwidth with this other technology. And the transition function is how the world is evolving from state to state, how these other technologies are changing, and how the radar itself is also changing. So once we have a POMDP, we can have this policy. And as you can see, the radar in red is changing its frequency to avoid any sort of interference from the jammer in blue, which would be any other technology. To further test the efficiency of this optimal policy, I ran some simulations, but the most important is that I also measured some additional metrics, specifically times jammed, which here you can see that the optimal policy does do the best. It does mitigate damage the best compared to some other more simple policies. But the project doesn't end here. I will be continuing this project in collaboration with Stanford University to further this optimal policy into a more realistic and real-world policy so that I can adapt it to a real radar and see how the radar not only adapts to the policy, but also interacts with real technologies in the real world. So not only will I be mitigating the bandwidth crisis, I will also be mitigating radar interference. Thank you.
Thank you very much. Who's got a question? Who hates it when Netflix doesn't work?
Whenever there's a jamming signal, how long does it take for the radar signal to switch to something else? Like, what's the time scale of like, bam, and then to the other thing? Like, how fast can I make my Netflix load if someone's on my frequency?
Yeah, so for this project specifically, the simulations would be one time step, which would be almost automatic, essentially. A radar can change its frequency very quickly. In a real-world application, it might take a little longer because there are other factors, as in other technologies, not just your Netflix and the radar. So.
One more question.
When you were learning your policy, did you assume that the jamming frequencies were like truly random, or did you follow some kind of model for it?
Yes, so I did follow a specific model for the jammers. So they follow the specific order that I created for them. Some of them were a little more random than others, but this was mainly to have the policy have to learn different types of like changing environments. But hopefully I can make it better at more random scenarios than it is now.
Thank you, Lucia.
Thank you.
Next, we'd like to welcome Gavin Morganegg from Utah State University. Welcome, Gavin.
Hello, everybody. My name is Gavin Morganegg. I am an aspiring rocket engineer and astronaut. One day, I want to be able to look out of the window of a spacecraft that I built at this incredible Earth and think about all the people that have helped me get here. My current progress along this goal has landed me as a rising senior at Utah State University, studying mechanical engineering with an emphasis in aerospace engineering. The purpose of this presentation is to demonstrate my passion for aerospace engineering and my desire to be a future leader in the aerospace engineering industry. I'm going to do that by talking about the effects of impacting a composite overwrap pressure vessel on burst pressure. And don't worry, all you biological engineers that presented yesterday, this will be really nice and easy to understand. By raise of hand, how many of you guys have scuba dived? Oh my goodness, that's a lot more than I expected. When you guys scuba dive, you guys know how heavy those oxygen tanks are. For scuba diving, they weigh upwards of 40 pounds. These are industrial pressure vessels. They're used to store various gases. You usually see these in industrial sites. And how these conventional Type 1 pressure vessels work is essentially engineers said, let's just put as much metal into this as we can, and it'll hold pressure. As a result, they're really heavy. As you well know, the aerospace industry is anti-heavy. We like light things. And a solution to that is to use composite materials. Composite materials are a mix of two different materials. That's why they're composite. Carbon fiber overwrap pressure vessels consist of three materials. There's a liner, usually a plastic liner, and this is to make sure that everything's nice and airtight. Wrapped around that is a structural composite layer, which is a carbon fiber, and then that carbon fiber layer is impregnated with epoxy resin. And this creates a really stiff and rigid pressure vessel that's about half as light as anything that you can find made out of steel. A drawback of this is that it's a brittle material, which means that even though it's elastic, it returns to exactly how it was before any deformation occurred. If you hit a steel pressure vessel with a wrench, you're going to see a dent. If you hit a composite pressure vessel with a wrench, what's going to happen is the composite's going to deform, the outside layer is going to bend in, the inside layers might break and fracture, and then it'll return to its exact same shape as beforehand. You can see the issue as you can't see the damage that happens. The purpose of the research that I conducted was to determine if barely visible impacts had any effect on the burst pressure of these pressure vessels. Now, burst pressure is important because you want to know when your pressure vessel is going to explode. So in order to do this, we took a 1 pound weight, as seen on the left, and it had a 1/2 inch impactor tip, and we dropped it from different heights onto the pressure vessel using the apparatus on the right. It's just a PVC pipe with a bunch of holes drilled in it. We impacted the sidewall, the dome, which is the round part, and the tangent where the sidewall and the dome meet at various heights, ranging from 1/4 foot to about 2 feet. And what we found was that, well, first of all, let me see, is this the laser pointer? Yeah. So we impacted it until there was detectable damage damage detectable to the qualified inspectors at the company that I was working at. This is considered detectable damage. And what we found is that after detectable damage was found, the vessel actually was able to withstand just as much pressure as it was able to before it was impacted. And even though this was the result, incredible care is taken when it comes to pressure vessels that have been impacted. Composite materials are very complex. There's a lot of different materials that go into it, and as a result, care must be taken when there's deformities or if there's any evidence of damage to one of these pressure vessels. But what this will help with is because of the cost of composite pressure vessels, we can disposition or determine what to do with pressure vessels that have been barely impacted. We can use them. We can use them even if they've been impacted, and we just have to take care to make sure that we use them correctly and use them in the right applications. Now, this is just a small portion of the big picture of a rocket or an aircraft. But as with what all of us are working on, we're working on little bits of something that comes together and becomes something incredible. And I would like to thank all the people that have helped me get to where I'm at. Hypercomp Engineering is the company that helped me do this research. I'd like to thank the Astronaut Scholarship Foundation for bringing me here. And I'd like to thank all the people who helped me get the Astronaut Scholarship. Mr. Schlichting, Dr. Anderson, and Dixon Nielsen. And I'd also like to thank my parents for dealing with me for the past 23 years. Thank you all so much for listening.
Thank you, Gavin. Who's got a question? There's a couple in the back that we haven't seen yet.
Sorry, I'll go real quick. But I was wondering if you were able to look at those lower layers and see if they were impacted like you expected, or whether or not it was just superficial on top.
So that is typically done using an ultrasonic sensor, kind of like when you get to an ultrasonic. And we didn't have the funding to do that for this, so no.
The question, is this also applicable to submersibles? Thinking, of course, and you just smiled, so you know exactly where I'm going.
Yeah. So this is an application of composite materials that is potentially safer and just a completely different application of composite materials than submersibles or the like.
So, thank you very much. Thanks, Gavin. And next, we would like to welcome Ian Rivera from Pennsylvania State University. Welcome, Ian.
Hello, can you guys hear me? All right, yes. Perfect. Let's see how this works. Okay, so hey everyone, my name is Ian. I go to Penn State University and I major in mechanical engineering. But during the summer of 2022, I got the opportunity to work in the MIT Summer Research Program in the Deng Energy and Nanotechnology group. There, I worked in the project called Tuning the Performance of Energetic Materials via Architected Channels. So, what are energetic materials? Energetic materials are materials that have tunable combustion performances, but they also produce large exothermic reactions. Because of this tunability, they are used in pyrotechnics, but also in rocket propellants. Now, the bad thing about these energetic materials is that the physics behind their combustion reactions are not well known. Because of this, we tend to use excessive material of these materials and then produce excessive pollution that we do not want. So this is where the tunability comes in and why it's important. The tunability of these energetic materials helps us evaluate the physics behind the combustion reactions of these materials and helps us evaluate the heat transfer mechanisms that govern these combustion reactions. Now, we are able to also tune these materials by not even changing the chemical composition of these materials, just by creating 3D pattern engineered designs. Now, these pattern engineered designs are important because they help us give us insight on the heat transfer mechanisms that help govern these combustion reactions of these materials. Now, a paper in 2022 published a theory that in these pattern engineered designs, there are different pattern pores which convection, the movement of hot air, helps penetrate the air and ignite the edges of these materials and increasing the burning rate of these materials. So, knowing this and trying to prove this, we come up with a research question on how can these pattern designs affect the performance of these combustion reactions. So to simplify this problem and to answer this question, we first created a 1D simplified model of these energetic material, this pattern design of energetic material, where we used a channel gap width of around 0 to 500 micrometers, which is what you can see there. I realize that's hard to see, but and then using this, we hypothesized that a material consumption rate of a minimal channel gap distance would be much higher than no channel gap distance in these materials, or a much higher channel gap distance in these materials because of the convection of hot air that penetrates through these pores. Now, to do this, we first formulated a nano-aluminum nanocopper oxide in 2-solvent solution, aluminum being the fuel and copper oxide being the oxidizer. We then 3D printed 3 solutions. Here I only 3D printed 2, which is the micro channel gap, which is a 10 micrometer width channel gap distance, and a 500 micrometer channel gap distance, which is the macro channel in our case. Then we set up this experiment in an imaging system to perform the experiment, and I developed a nichrome wire set up to ignite the experiment and collect data from it. So I basically just ignite the material, let it blow up, and gather data from it, which sounds pretty terrifying, but it's pretty cool. Okay, I don't know why that looks like that, but through this imaging system, we were able to capture ongoing snapshots of the reactions of 3 different energetic films. The first one you can see here is the fully dense energetic film. What you can see here, it's pretty interesting, is that the burning front is really uniform, and this is mostly because of the conduction of flame through the material, and that just spreads throughout the material very uniformly. Now, the film with the micro channel, which is the 10 micrometer channel gap distance, you can see the hot air piercing through these channels and igniting the edges, while then the flame spreads through the entirety of the material. You can even see this even more clearly in the macro channel gap, where you can see the hot air penetrating through here, the orange-black thing, and then igniting the edges of these materials and then spreading through the entirety of the material here, in which conduction takes over after it ignites the edges of this macro channel. So through these tests and ongoing snapshot reactions, we were able to see that the film with the micro channel, the 10 micrometer channel gap distance, provided a peak performance in which the material consumption rate or burning rate of the material was much faster and higher than the macro channel gap distance energetic film and the no channel gap distance energetic film. So what we could conclude was that using this simplified energetic pattern energetic design using a 3D printer, we were able to actually tune the performance without actually changing anything of the chemical composition of the material, and that the micro channel provided a much higher burning rate compared to the macro channel and no channel gap distance. And we believe this is due to convection of hot air through the pores that help ignite the edges of the material. But we need more tests and more 3D printed energetic designs with different channel gap distance to actually prove this, since it's really hard just to see pictures and say, oh, this is because of convection, this is because of conduction. So after this, we need to manufacture more of these designs and then test them, and then way at the end, like years and years, create a machine learning model to help predict this burning rate and the heat transfer mechanisms that help govern these reactions. So I'd like to thank Dr. Silly Dang, which was my PI during the summer 2022 at MIT. Soo-Young King, my mentor that was with me almost every day. Evan Bell, which is my undergraduate teammate at MIT, and my mentor and PI back at Penn State, Dr. Jacqueline O'Connor. I'd also like to thank the MIT Summer Research Program, the Millennium Scholars Program, which is my scholarship program back at my home institution in Penn State, and then the Astronaut Scholarship Foundation for giving us all this platform and this opportunity to talk to amazing people. Thank you.
Thank you so much. Who has a question for Ian? And then it was night. Who has a question for Ian?
Hi, Ian. I'm curious about the 3D printing. Did you find benefit or challenges with using that application to produce your models?
Yeah, so that's like a separate research topic by its own since it's so challenging. So what we do here is we use solvents to help increase or decrease the viscosity of the solution, to help it in cooling, to help it make it cool faster or cool slower, and to also make the material more uniform. As you can probably see here in the microchannel, it's not really that uniform. So this is mostly because of the unpredictability of just the manufacturing and the 3D printing of a liquid solution. Thank you for the question.
One more question.
Wait, was there somebody else? Sorry. What printer did you use to get this this kind of resolution in your 3D printed material?
Yeah, so I think it was just readily available Amazon printer that we bought. I wasn't there when they bought it, but it was something that we can all probably see in our labs. Nothing too complicated.
Thank you, Amazon, for everything. Thank you, Ian. Wonderful presentation. Next, we would like to welcome Mahiri Fernando to the stage. Thank you, Mahiri.
Good morning, everyone. My name is Mahiri Fernando, and today I'm here to talk to you about perceptual task-enabled guidance for helicopter use cases. So the main goal of this project is to combat some growing issues with military readiness. We're seeing an increase in complexity in missions as well as a lower retention rate in the military. And so this is causing for more errors overall, which can lead to safety issues as well as issues with mission success. And so the goal of this project is to develop an AI system, a headset that can be worn by operators to help reduce errors, improve performance, and enable the user to accomplish the same goals with little or no training. And so the main goals for this project is, what we'll talk about today is for helicopter use cases, but it's also being used for TCCC, which is emergency medical care, as well as maintenance, to help reduce some of the times. So some of the key technical challenges addressed with the PTG program is perceptual grounding, which helps recognize, which is where the machine is able to recognize objects and actions in a complex environment and be able to translate it into something that a human can understand, as well as knowledge transfer, so taking information from training documents, flight manuals, and checklists, and being able to convert them into something the computer can understand and then provide feedback to an operator. And so the main goal of this project was we took a pre-flight checklist for a UHH-60, which is a Black Hawk helicopter, and we introduced 84 different errors. And this checklist has over 200 steps and can take an operator about 30 minutes to complete. And so you can see all of the different types of steps that we did here. So we did some lapses, slips, and compounds, and you can kind of see here some of the examples. But what we did was we tried to skip steps, perform steps out of order, or perform novel or previously unseen steps, and we gauged how well the system was able to recognize these errors and provide feedback to the operator. And so here's the breakdown of each of the errors. You can see here we were able to do a majority of slips, which is skipping different types of steps and performing them out of order. We were unable to do a lot of the nuanced steps, which is what our future research will be focused on. But this was mainly due to limitations of the virtual reality simulation that we were working with. In future steps, we would hope to use an augmented reality system, which would allow for more of these nuanced errors. And so the first thing we tested was how well the system was able to detect these errors. And you can see once it detected it, how well it resolved them. So we had 3 different steps for how well it resolved the errors. A fully resolved error was both efficient and effective for the operator. An a partially resolved resolution was inefficient in its correction, but it still was able to recognize the errors. And then we were able to fool the system a few times where it was unable to resolve the error. And these are going to be what we're working on in the future to make sure none of these happen. But here's some examples. So if you were able to, if the instruction was to type a 1 in the keypad, you type a 0, the system is going to instruct you to clear the keypad and type a 1. This is the most efficient because it's the fewest button clicks. A partially resolved, this is for a specific screen. So if you hit the wrong button to get to the wrong screen, it's actually going to take you all the way back to the initialization page, step you through the subpages to get back to that main screen. And this is inefficient because an actual pilot is just going to hit the previous button to go back a step and then go to the right screen. So the machine wasn't able to recognize that easier step, and therefore it's partially resolved. And an unresolved step here is if it asks you to type an 8 and click enter, but you type nothing and hit enter, it actually got stuck and was unable to advance. And so this is what our future model is going to hopefully be able to detect. So here's some of the qualitative observations for what we were able to resolve. You can see here something of importance for its instructional utility. So the machine was actually able to track your hand and eye movements, and it was able to notice that if your finger was going in the wrong direction, it would flash a pay attention screen to kind of prevent errors from happening before the user pushed it. And this is essential because it can help stop a user from making a mistake, which a co-pilot would not be able to do. And then another thing for intelligibility, there actually was a green hand overlay that would point at the correct button for the user to push. And this was important because instead of looking at a whole screen of buttons and trying to determine which one to push, the user could zoom in on exactly which one. And this kind of reduced some of the time it took to make some of the steps, and therefore would overall decrease the amount of time that it took a user to complete the checklist. So this program is currently in year 1 of 4, and so we're currently working with just the pre-flight checklists. Ocarina, which is the name of the system, we're going to be moving to teach it multiple tasks at the same time, so we can handle a lot more of the task saturation that a regular pilot is dealing with. We're also going to be training it on emergency procedure data sets, which is where a pilot's going to be under a lot more stress. And we're hoping to decrease the reaction times in these high-stress environments to reduce accidents in helicopter use cases. Thank you. I would like to thank Lincoln Laboratories, especially Maggie Grohl and Marianne DeAngelis, my advisors on this project, as well as Northrop Grumman, who provided the AI system that we worked with and tested. I'd also like to thank the Air Force Academy and the Astronaut Scholar Foundation for providing the funding for this research topic. Thank you.
Thank you. We have a question.
Really good. I really liked what you just showed. It was really great. Just a couple of questions. First, what was your training data set? Like, how big was it? And how do you avoid overtraining or undertraining of your model?
Yeah, so the data set that we received was already trained, and it was trained using a variety of pilot data. So they took advanced experienced pilots as well as novice pilots who weren't in training, and that's the initial data that it received. It also was limited by the virtual reality that I said, so all of the buttons that were pre-programmed, that was also used in the training.
Next question.
Hello. I was wondering, without the headset, just in general, what are the frequency of, like, on, say, like, any, like, the total amount of missions, how many of those missions will a mistake happen, how often are they, and how do they vary according to factors like stress, complexity, pilot skill, etc.?
Right, so that's the next phase of this project, but we're going to basically be checking how it reacts to pilots of different experience levels. And we're also going to be making sure that the headset we're using, it's currently, it's the most up-to-date virtual reality headset that we're using, but we're going to be shifting into an augmented reality headset that's going to allow for more testing like this to be done.
Thank you, Mahiri, and thank you for your service. And as soon as that flashing button that prevents you from making a mistake comes available, call me. All right, our next presenter is Jim James from the Georgia Institute of Technology. Welcome, Jim.
Hello? Can you all hear me? Cool. Good morning, everyone. My name is Jim, and today I'm excited to talk to you about my summer research project that I did at Carnegie Mellon, dense depth completion for programmable light curtains. And I had the pleasure of working on this project alongside Karnik Ram and Dr. Srinivas Narasimhan of Carnegie Mellon's Robotics Institute. So before getting into the project itself, I'd like to briefly talk about the importance of accurate depth data in a variety of situations. So primarily in human-robot interaction situations, we find that having accurate depth data of the scene is incredibly important in ensuring the safety of humans. You can imagine for advanced driver assistance systems, such as autonomous vehicles, being able to detect the precise location of a human can be the difference between an accident and a near miss. Likewise, there's similar cases in robotic manufacturing where being able to detect precisely where a human is can prevent an injury. So it's really important for us to be able to get this information. However, it turns out it's actually rather non-trivial to get it. So the canonical way of acquiring depth information in the literature is through LiDAR. But LiDAR actually comes with some pretty significant downsides. The first of which is that it's extremely expensive. A high-resolution LiDAR device can range from tens of thousands, if not hundreds of thousands of dollars, which means that immediately many commercial and consumer uses are no longer viable. And in addition, even compared to the camera on something like your smartphone, LiDAR devices are actually rather low resolution, even if you go for one of those higher-end models, which can then limit the usability, especially for objects that are far away from the camera or small objects that are nearby, such as a human child. So to try to resolve this issue, a lot of research in recent years has been focused on a problem called monocular depth estimation, where instead of using a specialized sensor like LiDAR, we simply use a RGB camera equivalent to that like on your phone. But this actually comes with its own set of challenges. And the main issue with this is that it's actually an ill-posed problem. And by that, what I mean is that for a given RGB image, there are actually infinitely many scenes that correspond to the same image. So you can have actually many different values of depth that were all valid. So you can't actually precisely solve this problem, meaning that if you want to use it for a safety critical task, you may not necessarily be able to guarantee safety. So to try to work around these issues, we instead investigate the use of a novel sensor developed by Carnegie Mellon's Imaging and Illumination Lab called a programmable light curtain. And this sensor is pretty unique in that it has both high resolution as well as low cost. So this sensor relies on a laser and a standard infrared camera. And what it does is that it can scan depth along a user-specified 3D ruled surface. And what this means is that if you were to take something like this curtain profile and we extrude it vertically, any points in the scene that are touching that curtain would then be detected by the device. So we'd be able to get a partial point cloud of the scene in high resolution, and we can do up to 45 of these user-specified surfaces per second. So this is not a perfect solution in itself, because in a sense, it's only giving us sparse information since it only tells you points that are along this curtain. So the ultimate goal of this research is to come up with a solution that will allow us to incorporate the information from a programmable light curtain into a network of some sort that can predict dense depth of the entire scene. So the first step towards this goal is to actually come up with a way that we can choose the curtain that we are trying to sample from. And there's a variety of different techniques, but the technique that we ended up settling on is called random curtains, where basically we randomly generate these curves in order to best predict different areas in the scene. So going from there, we then use a diffusion model, which is a popular generative model, in order to predict dense depth values. So it's a very brief explanation on diffusion models. Basically, these models work by going from a distribution of white noise, so Gaussian noise, and then predicting an image based off that, while also doing this in an iterative fashion. And the reason why this is really important for us is that they can predict high-resolution outputs while also leveraging the iterative nature of the light curtain, so we can use the updated information at every step in order to get better predictions. Let's get these. So this work is still in progress, and one of the big challenges of using a diffusion model is that they're slow to train. So as of right now, we don't have final results. But nonetheless, we do analyze some challenges and limitations. So one of these is that the inference speed of diffusion models is somewhat slow, at least with the current setup. So for certain low power tasks, this may not be necessarily viable. For instance, if you're using a embedded platform or something like that, it may not necessarily run fast enough. And currently the formulation is only limited to static scenes. However, future work might look to ease that restriction because we have seen a couple of works that have been able to extend diffusion models to non-static scenes. And we also plan on incorporating the design of curtains in addition. Thanks for listening to my presentation. Happy to take any questions.
Thank you, Jim. Questions? I see one towards the back.
Thank you for your presentation. I'm curious, the curtain itself, is it essentially a cascade or is it a mesh design? And if it is not mesh, would using more of a mesh model increase the viability of the solution?
So it's sort of like a mesh model. Basically, the way that you can, let me go back to the system diagram, that might help. The way that you can think about the curtain is that it's basically just tracing out this ruled surface in 3D. So if you were to take that curtain profile and extrude it vertically, each point on that curtain profile would be effectively projected onto a pixel on the imaging sensor. So in a sense, that's kind of like a mesh because every pixel would then be, if you back project it into the surface, that gives you like your vertices on the mesh.
Another question.
All right, awesome talk. So conditional diffusion models are awesome and very novel, very powerful, but prone to hallucination if I'm not wrong. So I'm wondering if you're using this for like safety, like putting this on a driverless car, how can you get your model to quantify uncertainty and tell you whether or not it's actually sure if there's a person here, or tell you, I'm sure there's a person here, but maybe within this 5-foot radius?
That is an excellent question. And one of the big advantages of using something like a conditional diffusion model is really taking a step back and thinking about what generative models are. Really what they're doing is that they are explicitly modeling some sort of probability distribution on their output, right? Instead of just giving you a point estimate. So the advantage of this is that if you combine this with some sort of sampling technique, such as pick your favorite Markov chain caller, for instance, you can actually get good uncertainty estimates because you're effectively getting an estimate of the probability distribution, which in turn you can use that in order to quantify uncertainty. And this is actually very interesting, and I'm glad you brought this up because that actually leads into some of our future work that we're planning, which is using that uncertainty to then design the next curtain to sample.
Great. Thank you so much, Jim.
Thank you.
Next, we'd like to welcome Maya Odom from North Carolina A&T State University. Welcome, Maya.
Hello. Hello. Okay. Hello, my name is Maya Odom, and I'm a hardware development intern this summer at Amazon Smart Vehicles certification team, and my project is on soak test automation. Quick introduction to me. I am an honors senior computer engineering major at North Carolina Agricultural and Technical State University. I studied abroad last semester in Cyprus at the University of Nicosia. And I have interned at Amazon, the Walt Disney Company, the Carnegie Endowment for International Peace, and Chevron. A quick background about my project. My team at Amazon certifies Alexa to be in partner vehicles. And so when we certify a car to have Alexa in it, a lot of times after that, a partner will send an update, just like you get on your phone over the air. And those updates will inadvertently affect Alexa. And so they cause, at times, in the field failures for already certified features. So my team had to investigate why that was happening, and we found that there was a gap between the certification process and when updates are being pushed. So we needed to find a test that'd be easy and quick and easy to understand to fill this gap. So we decided to do a SAIC test. A SAIC test is known as an endurance test, stability, sanity check. It's very well known in the, we'll say, this field. And it's used to detect performance-related issues. And in a sense, it lets the device soak for a period of time by giving it a variety of test scenarios over a period of time. And we use it to test the robustness of the Alexa features for the vehicles that are already on the road today. So something that's already been certified by our team, we're going to use it to just verify everything is working properly. And we use a test tool to make sure that it can be run autonomously, so that way we can run the test and go, which can save hundreds and thousands of hours of time for testing. So how I developed my project was, first I had to curate all of the test scenarios that could be automated, which means specific test scenarios that could be used hands-free, like asking Alexa what time is it, but asking Alexa but you can't use a test scenario like registration because you actually have to tap the screen and follow steps. And I had to curate all of those scenarios for all the different locales I was working in. So English for the United States, English for India, Japanese, and German. And then I had to record the audio files for all 4 locales and determine the wait time between each scenario, because if you have a scenario that is, you want Alexa to be barged in, you want to interrupt her while she's talking, you have to make sure that time is accurate. But on the reverse side, if you don't want her to be interrupted, you have to make sure that timing is accurate as well. The next step was to develop an outline file to understand and outline all the important features and all the important information you want Alexa to interpret, and I'll go over that when I show my results. And then to configure my hardware, I needed a speaker, a test phone, a Raspberry Pi, which is a standalone computer, which we use because you can keep it running and then go. You don't have to keep it running on your laptop. And then a test bench, which is generally just the infotainment system of a car. You can also run this test in a vehicle, but the test bench makes it more portable and quicker to use. And then, of course, run my test and figure out why certain scenarios are failing, all the way up till I got to a 95% accuracy rate. So I can't show my demonstration because of proprietary information, but I can show my results from the demonstration. And so I have a successful and failed test case. And as you can see on the left, it shows the information that would have been outlined in that outline file of what Alexa is expected to hear. So for this case, it's Alexa, call John. How she is expected to respond. So she's supposed to say at least the name John, which is, and then also you have on the right side the result. So you have that Alexa woke to her name, she understood the command. You also have how she responded, the intent. So that shows how she was able to interpret the command, and then also, again, what she heard. And same, even when the device failed, so by failure, I mean that the device did not give the expected response, but still you can understand what happened. And so this is the key part of the automation part of the project, because now you don't have to be there watching the test run, and you can just come back whenever you're ready and see the results as if you were there. And so, again, you have the expected response for this one. For this example, I was using a test bench that did not have car controls. If I was in a vehicle, it would have probably worked, but it has setting, the expected response for this one was setting the temperature to 68, but she said that I can't do that because I don't have car controls. Overall, this project also illuminated a very key tool that could be used internally at Amazon, which was that this project can be used to create a trend line to see how Alexa is operating over a period of time, because before then we didn't really have something to test a daily check to see, a consistent daily check to see how Alexa is operating. And so now not only can we give this tool to our partners, which was the intention of the project, but also we can use it to track how it's happening. So this is a test I did for 2 weeks every night. And as you can see, no test went under 95% accuracy. And this again shows that the test is overall consistent, and that, again, if something does go wrong and we do get it in the field failure, now we have our own data to go back to and understand why it happened. Some key takeaways is we were able to first fix the problem, we were able to fill in the gap and understand what happens before and after an update. And then secondly, like I stated earlier, we can know what's happening before it hits a partner or even in the field. And then just a couple of next steps. I'm still technically working at Amazon, and so we're launching this program for specific partners for US English, as well as expanding and finishing the tests for other languages and trying to expand always. I'd like to thank everyone on my team at Amazon, my mentor, my manager, as well as A&T for helping me get my internship, and the Astronaut Scholarship Foundation for allowing me to present today. And I'll take questions.
Thank you, Maya. Question.
Hi, Maya. Thank you very much for your presentation. I'm curious about your input samples. Did you use native speakers as well as non-native speakers? And if you did you see any significant difference in outcome?
So the way that we were running this test, we only used native speakers. So for US English, you had to be native to the United States. For Indian English, you had to be native to India and speak English. Same for German, you can't just speak German, you have to be a native German and Japanese. And it was funny because all those people happened to be in my lab, which is not necessarily the case for other locales. But we didn't want to use non-native speakers because we were using partner benches that were also native to that country.
One more question. No? Here we go.
No. She's always evolving, and so that's why also we need this test, because as I showed in my graph, that one day, this was the same test that I was running over a 2-week period. One day was at 98%, the next day was at 95, or the reverse. And that's not necessarily because Alexa was broken, that's just because we're always updating the software and making her hear list better. And there are some times when one group of commands may not be working because they're working on an update for her. And so that's why, again, this test is important, because we have our own data. So if at one point she's not listening to what time is it, we'll know before a customer does.
Thank you so much, Maya. Does anyone besides me argue with Alexa? Just curious. Welcome to Joshua Baston from the University of Wisconsin. Welcome, Joshua.
Thank you for the introduction. My name's Josh, University of Wisconsin-Madison. I've also done some research at the Karlsruhe Institute for Technology in Germany. And today, my goal is to convince you that molybdenum alloys are the future for better jet engine efficiency. A little bit of background. So jet engines, it's a mix of a rocket and a big fan. You got blades that suck in cold air, a combustion chamber, and then you shoot all of it out the back. They get really hot, and the materials inside need to survive extreme heat. You need to survive the centrifugal forces. They're spinning terribly fast. And they also need to withstand corrosion from the gas, the sulfur, all the stuff that's going on the inside. Ever since like World War II, we've been using nickel. Incredibly impressive alloys. 718, as was talked earlier, is a nickel superalloy. And right now, they can handle up to 1100 degrees operational. Why does that temperature matter? Well, the hotter you can run an engine, the more efficient it becomes. Without diving into all the thermodynamics, we basically can see as we increase our operating temperature, we get higher power output per kilogram of fuel. So right now, we have metals that can operate at 1100 degrees C, but to get above 1100 degrees C, at least operational temperatures, we have to add in cooling. So we can add in thermal barrier coatings on top of the metal, we can add in cooling chambers, all to make sure that the metal never gets above 1100 degrees C. And while we do get more power out of this, we start dropping off of the ideal performance curve because those cooling methods are not free. They do take energy. If you scale this up to worldwide commercial air flight, we lose about 100 million tons of fuel a year purely off of inefficiency losses from these cooling. So how do we fix this? Well, we need better metals that can operate at higher temperatures. And that's where my research comes in on molybdenum alloys. So pure molybdenum, incredibly high melting temperature. 2,600 degrees Celsius, it's almost up there with tungsten. It is incredibly strong. The density-specific strength is 1.5 times that of nickel, and that does scale into the alloys as well. The big issue with molybdenum and all the other refractory metals is they fail catastrophically with oxygen. So you get at 700 degrees Celsius, they react with oxygen, they form a molybdenum trioxide, which is a gas, actually, above 500 degrees Celsius. And your part will literally vaporize in front of your eyes, and it's sad. So how do we stop molybdenum from doing this? Well, we can add silicon and boron to the alloy. When we do this, just as like an as-cast alloy, we get a separation into a few different intermetallic phases, all still with melting temperatures above 2,100 degrees. These intermetallic phases are a little bit brittle, and they would need to be stabilized, or what I specifically look at, applied as a coating. So to apply most of alloys as a coating, it's a 3-step process. The first thing you do is you need a fresh sheet of molybdenum on your surface. If you have a different kind of alloy underneath or even a whole different substrate, you can basically create a spray paint of molybdenum. You take very fine 1-micron powder, some other fancy chemicals, and you can spray it on, bake it on. Then we put it in a chamber with a bunch of silicon and boron gas. It's called a pack sedimentation process for those in the aerospace industry. And what we get is this picture on the right. We get the silicon and the boron. They diffuse into the surface a little bit. How far depends on how long we bake it. And we see the separation of a molybdenum disilicide layer, one of the intermetallics I mentioned, and some molybdenum boride. And then the third step is we actually then purposely expose it to oxygen, which might seem a little bit counterintuitive. But because we added that silicon and the boron into the surface, we actually draw it back out, and we get an amorphous borosilicate glass on the surface. So that is the same material in all your beakers, all your other lab equipment. It's known for being very unreactive, can withstand up to 1,600 degrees before it experiences some melting and some structural defects, and it completely protects all the other phases that are below it. And then what that looks like when we put it in a furnace for long periods of time, uncoated sample, mass loss is extreme. Like within a few minutes, it's gone. But our coated samples can survive many, many hours, and we have some samples that have gone up to 1,500, 1,600 degrees, and they have not had any mass loss for 100, 200 hours. So, as a quick recap, jet engine efficiency is largely helped by the ability to go to those higher temperatures. Nickel alloys have been used for the last 70, 80 years, but they have started to stagnate in their improvements. And I personally believe that molybdenum alloys are the future for how we move past this. I specifically want to acknowledge my professor, John Parapesco. I'm an incredibly annoying student, and I do not know how he deals with me. I'm still in his lab, surprisingly, along with some of my other funding agencies and, of course, the Astronaut Scholarship Foundation. And with that, I will open it up for questions.
Thank you, Josh. Question. Nathan is delivering the microphone.
So you mentioned that the silicon and the boron can kind of diffuse into the molybdenum a little bit. And then particularly when you draw it back out, have you found that this impacts the mechanical properties at all?
Yes, so that's a really good question, and you can actually see it here in the photos. So these are like voids in the surface now. So we draw out some of that silicon and boron, it leaves a void. And if the surface is damaged, like let's say sand gets sucked into your jet turbine, big problem in the Persian Gulf War, we can draw it a little bit more, but eventually you can't. And there are some structural problems with that. The nice thing is the structural properties are not coming from the coating. They're coming from the molybdenum. like the substrate. So, 20 microns of damaged, maybe not as strong, not that big of a deal.
Question.
One more question.
I was wondering, because you showed the graph of the mass loss and how when it was coated, that it lasted for 50 to 100 hours. I was wondering how much longer and how much more stretched out would you need that graph to be in order to actually be installed on real jet engines that don't vaporize?
So that's a really good question. Current jet turbines get their blades replaced every 2 years, and they're operated pretty much 24/7 because docking fees at airports are extremely expensive. So you need thousands and thousands and thousands of hours. However, good luck getting a PhD student to stay that long. So we normally, the industry standard, or at least the academia standard, is you test up to 100 hours or you do like 1,000 hours. And you don't really do anything in between, and you won't really see any papers published outside of those two numbers.
Okay, thank you, Josh. We did not find you annoying at all. I just want to take one quick minute to thank our ASF volunteers who are working to get your questions answered. Thank you all for running around with the microphones. We appreciate it. Our next presenter is Annika. Oh, yeah, absolutely. Thank you. All right. Well, let's welcome Annika DeVol from Clemson University. Welcome, Annika.
Good morning. My name is Annika DeVol, and I am a senior at Clemson University studying material science and engineering. And today I'm going to talk to you a little bit about my work with joining ceramics and high-temperature ceramic matrix composites using polymeric precursors. So developments in the field of high-temperature ceramic matrix composites, or HTCMCs, are important for further developments in aerospace propulsion, as well as nuclear energy conversion and other thermomechanical applications. And HTCMCs, one method of producing these that is proposed is using a polymer to ceramic conversion, and this would allow for easier processing techniques. Polymer processing techniques are typically a little bit easier than ceramic processing techniques, so this would allow us to process it as a polymer and then convert to a ceramic. And this can be done by taking a polymer that contains silicon, oxygen, carbon, or nitrogen in its backbone, heating it through a process called pyrolysis, which is thermal degradation at elevated temperatures in an inert environment, and this facilitates the polymer to ceramic conversion. And so we can create any of these ceramics here, as well as their composite materials, but today I'll be focusing on silicon carbide. So the overarching goal of the project is to use a polymeric precursor for silicon carbide to create and join ceramics in high-temperature ceramic matrix composites and evaluate those joints. So when I say joining them, I say just two pieces of ceramic and sticking them together as an organic adhesive, and it's just one organic system. And the objective of my particular work that I'll be talking about today is optimizing spray coater parameters in order to create a thin, even, uniform joint. So I used a homemade spray coater and changed 3 different aspects of spray coater function. The first was cylinder pressure, so this is the argon gas pressure used to atomize the precursor, and I tried this at 40, 60, and 80 psi. Then I changed rail speed, which is the speed at which the nozzle moves across the substrate surfaces, and tried this at 25, 30, and 35 millimeters per second. And finally, I tried changing syringe rate, which is the rate of precursor delivery into the argon gas stream, and tried this at 1, 1.5, and 2 milliliters per second. And I used a silicon carbide matrix precursor that is a polycarbosilane polymer as my precursor, and used scanning electron microscopy as well as a 3D optical surface profilometer for characterization. So I started by coating the samples, allowing them to cross-link in an oven for 24 to 48 hours and cure, and then just evaluated them visually to start, and broke them down into 3 different categories based on their optical quality, just based on looking at them. So this picture on the left, there's a nice, thin, even coating with minimal wrinkling of that coating. But then with the picture on the right, you can really see that coating along particularly the right sides of those microscope slides that I was coating. And so from this, determined that the syringe rate has the most prominent effect on the quality of the coating, and then moved on and took a few samples to SEM for further analysis. So here I was just looking again at that uniformity and assessing that uniformity at just a smaller scale, and got some preliminary measurements on thickness, so around 30 micrometers, but this was just a preliminary measurement of thickness. I then took it to a 3D optical surface profilometer to obtain a more precise measurement, and got around 53 micrometers here. So concluded from this work that the best coatings are obtained at the cylinder pressure of 80 psi, a syringe rate of 1 milliliter per second, and rail speeds of both 30 and 35 millimeters per second are effective in obtaining these thin, even coatings. And these are the two best samples that I got from those runs. So there's quite a bit of future work to go off of in this area. The first thing we want to do is demonstrate the repeatability of these coatings that I've already made, and also evaluate ways to precisely control that thickness, and then from there, figure out what exact thickness we want for our joints. So I was just working with coating glass microscope slides in this stage because I wanted to save on costs. I also wanted to be able to break those slides and look at the cross-section of the coating under SEM. So that's why I was doing that there. But then when we start moving onto our actual joints, we want to know what thickness is best for these joints. And then we will start adding a chemical called dicumal peroxide, which is a cross-linking catalyst. And this will ensure that the polymer is completely cross-linked before we move on to the pyrolysis process. And so we'll take these two ceramics, join them together, cross-link, pyrolyze, and then bring it to a ceramic, and then evaluate those joints, the mechanical properties at both room temperature and elevated temperatures. And finally, one major issue with this pyrolysis process is a shrinkage that occurs during the process. And this can be between 60 and 80% volumetric shrinkage, and this results in cracks in the coatings. And so we want to assess methods of reducing this shrinkage. I want to thank Professor Bordia for allowing me to work on this project and his guidance throughout the process, as well as Lee Williams for his supervision and training. And also thank you to ASF for bringing us all here and allowing me to present today. And at this time, I can take any questions.
Thank you, Annika. Where's our first question?
Coming from a background that knows like nothing about this, what are you using this for and why this material?
Yeah, so this is going to be used in aerospace applications. It could also be used in nuclear energy applications, just really anything that's high temperature. It could be used in an engine, it could be used on the outside of an aircraft, things like that. We're particularly interested in silicon carbide as this can go up to 1600 degrees Celsius. And this is about, I only know actually, it's like a 300-degree increase from what current high-temperature ceramic matrix composites can withstand. So we want to just get it up to a higher temperature than we were able to achieve before.
One more question.
Do you think that you would have better adhesion to the ceramic surfaces as compared to the glass microscope slides that you were using? Or do you predict that that's just going to be a pretty similar process?
So it should be better adhesion, and actually with these glass microscope slides, I didn't do any sort of surface preparation, I didn't do any sort of like grinding or polishing, and that's something that we would do moving on to the ceramic surfaces to make sure it's properly stuck on there. But it should be better with the ceramic surfaces.
Annika, thank you so much. The next presenter we're welcoming is Lucien Tsai from Harvey Mudd College. Welcome, Lucien.
All right, hi everyone. I'm running on chocolate, so let's see how that goes. And my name's Lucien Tsai. I'm a rising senior physics major at Harvey Mudd College, and today I'll be presenting my work, which I also did at my college with my advisor, Professor Mark Ilton. And my presentation is on how viscoelastic materials are most energy efficient when loaded and unloaded at equal rates when stretching. And so the main kind of theme of this project, the motivation, is why animals use biological springs during motion. And biological springs, in this case, can comprise of tendons or even like the chitinous exoskeleton materials. And so basically, to answer this question, there are two parts. The first is energy conservation. And these are energy-conserving motions, so they're very cyclical with roughly equal loading and unloading rates. And you could just think of what happens to your tendons whenever you're walking or running. They basically have similar loading and unloading times. And the second answer is power amplification. So by using elastic storing energy and elastic mechanisms, we could achieve ultra-fast movements. And a good example is the figure shown on the right here, which is a mantis shrimp. Mantis shrimp basically has a biological hammer, and once it's released, it could hit a target, and even in like a lab test, it could even break a glass panel. And ultimately, these types of movements are very asymmetric. In this case, it's a long loading time versus a very fast release during unloading. And so the two questions we have is, do elastic biological materials behave differently when doing symmetric motions versus asymmetric motions? And the second question we want to answer is, what physical principles govern the performance of the material, particularly its energy efficiency during these types of motions? And so the methodology we use is, first we use resilience. This is our metric for energy efficiency. And it's a very simple metric. It's basically the energy released during unloading over the energy stored during the loading phase. And the samples we used are twofold. The first is a tendon obtained from the frog you see on the right figure right there. And we also worked on synthetic elastomers. In particular, the samples for synthetic elastomers presented here today are for polyurethane elastomers. And so these are our results by conducting the tests on the frog tendons, both at symmetric and asymmetric rates. So you can see from the figure A, that's an example of symmetric rates. You could see the orange curve shows the displacement versus time. So you could see the same loading and the same unloading. And while after you apply this strain versus time waveform to the material, you could get the stress response from the blue curve. And from the strain versus time and stress versus time, you could put that into a stress versus strain curve, as shown on the gray curve right there. And while figure A is an example of symmetric motions, figure B is a good example of a very asymmetric motion with a 10-second loading time and a 0.1 second unloading time. And basically, once we calculate all the resilience of all these different motions at different loading and unloading times, we could construct a heat map as shown at the figure C. And basically, from figure C, we could see that a higher degree of asymmetry in the motion reduces the resilience of the material. And in this case, it's about a 20% reduction in the energy efficiency of the tendon we tested. And so more asymmetry in the loading and unloading rates decrease the energy efficiency of the tendon we tested. And so although tendon is a very nonlinear material because it has a very hierarchical type of structure to it, we also wanted to make this as a universal principle. And to do that, we used synthetic elastomers, and we particularly stretched it at a maximum strain in which it's still within the linear viscoelastic regime. And so we used a polyurethane elastomer, and so the very left figure on the left for panel A is basically the same test done on a polyurethane elastomer. And practically, we see the same effect. A higher degree of asymmetry results in a lower energy efficiency. And everything to the right of it is basically the modeling technique we use. So we use a generalized Maxwell model. And using this model, we could basically have an excellent agreement with the experimental results. And the computational results are shown in the middle panel of figure A. And from this model, we could also extrapolate the limiting behavior. So very high loading and unloading times and very low loading and unloading times. And that's what you could see on the rightmost panel of figure A. And you could see the better distribution of behavior across this larger time scale. And so ultimately, this conclusion is that a similar asymmetric effect is found in synthetic elastomers, not only in polyurethane, but we also tested other ones as well, such as neoprene and latex. And this behavior could be modeled by a linear viscoelastic model. In this case, it's the generalized Maxwell model. And so these are my references, and I would like to acknowledge the funding source from the Harvey Mudd College Physics Summer Fund, and also our collaborators at UC Irvine for providing the frog tendon samples, and also my lab and my advisor. Thank you.
Thank you. Who's got the first question?
Hi, really nice presentation. I had a question. So you were saying that the asymmetric loading can be less efficient, but in biological systems, do you normally find that asymmetric loading is used for higher forces, like maybe an insect or something like that, that kind of like a low gear of a bicycle, something like that?
Yeah, so more asymmetric motions are primarily used, at least for biological systems, for more smaller scale organisms, because we do find a kind of like a trade-off. If you can imagine using muscles or motors to actually create ultra-fast motion and high forces, it's gonna be, it's not as efficient as compared to using a very elastic mechanism, where you could have very fast unloading rates to achieve like a high energy impact.
One more question. Anybody? Frog tendon? Tastes like chicken?
Is there any application of this? I'm just wondering if the application is like to synthetic tendon replacements for animals or people, or if there's another application.
Yes. Yeah, so basically a big goal of this is to understand kind of like the mechanical energy efficiency of tendons. So by understanding how the energy dynamics works during whenever we're like walking or running and doing asymmetric motions, we could better understand how to create synthetic materials to better match the mechanical behavior of actual biological tendon.
Great. Thank you so much, Lucien. Do you know what time it is? It's break time. We're running quite on schedule, so please take 5 minutes and please do return in 5 minutes. Thank you.
Oh, okay. Are you like leaving the thing? Sure. Yeah, that's cool. Oh, just like as opposed to knocking it back? I don't really, I like cut caffeine out of my diet. I want to like do it until I'm healthy. Really?
Like, hello, how's everyone? Like, I want it.
Hi, everybody. We're done with our break. Please take your seats.
Carol's on such a tight schedule that I'm like, I better not.
Okay, final stretch. Take your seats, please.
There's your notice. I don't know.
Welcome back. Welcome back. Alexa, seat the scholars.
That is not how I operate.
Alexa, seat the scholars. She did it, sort of, mostly. All right, we have 9 more fantastic presentations to listen to. So again, thank you to everybody who's gone so far this morning. You're absolutely fascinating and so many different questions that are coming up in my mind. So let's head back into the final stretch of this year's technical conference. And let's welcome Isabella Dressel from the University of Virginia. Welcome, Isabella.
Hi, I'm Isabella, and I'll be sharing work that I did this summer at NOAA PMEL on evaluating ensemble forecasts of Arctic air-sea fluxes using sail drone observations. So air-sea interactions represent exchange between the ocean and atmosphere, and they play a major role in global weather systems and the surface energy budget. Now recently, rapid warming and a decline in Arctic sea ice has modified trends in surface turbulent fluxes like latent and sensible heat flux. Now, latent heat flux is the energy transferred to the atmosphere due to the evaporation of water, and sensible heat flux is exchanged due to the air-sea temperature difference. Now, these fluxes need to be accurately quantified by our observations and models so we can predict how the Arctic will warm. But our ability to validate Arctic predictions has been limited by our in situ observations, and this is because the seasonal migration of sea ice prevents us from using conventional platforms at fixed locations. Now, sail drones are uncrewed vehicles that are driven by wind and powered by solar energy, and because these are mobile platforms, they enable us to gather these observations in areas where conventional platforms can't be used. So we use these observations from sail drones to validate ensemble forecast from the European Center for Medium Range Weather Forecasts, or the ECMWF. So these ensemble models have lead times up to 15 days, and they differ from your standard deterministic model in that they have several possible outcomes, which in our case is 50. So these 50 members have slight perturbations in your initial conditions right here, and this allows them to capture a wider range of forecast uncertainty and also possibilities, especially at those later lead times. So I'll first show a little bit of a demonstration. So this is just showing a time series of latent heat flux at different lead times. So we have the interpolated ensemble members in gray, the ensemble mean in blue, and the sail drone observation in orange. So we see that the difference between the predicted and observed fluxes starts out quite small, and it tends to grow with increasing lead time. Now we also see changes in the ensemble spread, which describes the range of uncertainty in the model. It's also important because we want the spread to be large enough so that the forecast is capturing the full range of observations. Now we can already start to see here that that's not always the case. So we first looked at the forecast skill, which describes the accuracy of the ensemble. So I correlated the ensemble with the observations as a function of lead time, and I have that shown here on the left for latent heat flux in blue and for sensible heat flux in red. We see that for the ensemble members, these correlations become insignificant around lead times of 4 to 5 days, whereas for the ensemble mean, they're significant to later lead times. We can also look at the spread skill relationship through the normalized RMSE and spread. So ideally, we want these to be close together because this would mean that our model is capturing the natural range of variability, and as we can see, that's not the case here. Also, once the RMSE surpasses 1, the forecast is no longer skillful or accurate because the errors are outside of 1 standard deviation of the observations. And based off of all of this, we see that the forecasts lose their skill or accuracy around lead times of 4 to 7 days. I then wanted to look at the statistical consistency of this model, and I did this based off of a rank histogram. So this can show us if the ensemble has any low or high biases, and if it's capturing the full range of the Saildren observations. So to make this histogram, I first ranked the ensemble members from low to high, and then I ranked the Saildren observation within that distribution of the ensemble members, and I create these histograms from the observation ranks. So what we see for the fluxes is this U-shaped distribution. Now this tells us that the forecasts are underdispersed and overconfident because these Saildrens are often falling near the first or last ranks, so they're often at the extremes or outside of the distribution of the ensemble members. We then confirm this by looking at the probability density functions, which are shown here. The PDF for the ensemble in blue is very narrow compared to that of the Saildren observations. So finally, we wanted to know if we could explain the errors in this model. So we know that sensible heat flux depends on wind speed and the air-sea temperature difference, and latent heat flux is driven by wind speed and the air-sea humidity difference. So it's possible that errors in these variables are contributing to errors in the model. So to answer this question, I used time series regression, and briefly those results are shown here. So we found that for sensible heat flux, these errors are largely being driven by errors in the air-sea temperature difference, whereas for latent heat flux, they have similar contributions from errors in wind speed and the air-sea humidity difference. Now this is really important because understanding where these errors are coming from in the model is one way that we can work to improve them in the future. Lastly, I would like to thank everyone at NOAA PMEL for supporting me this summer, and this work was funded by the NOAA Hauling Scholarship Program. So thank you so much, and I'd be happy to answer any questions.
Thank you, Isabella. Let's have a question.
Hi, great talk. Was curious if you could expand on how your model performs with other environmental variables?
Yeah, so it performed pretty poorly for the fluxes, as we saw. I showed an example on the first slide for pressure, which is something that the model performs better for. So for pressure, it varies more cohesively in space compared to the fluxes because it's dependent on the weight of the whole atmospheric column. So for something like the rank histogram, we saw that it was actually able to produce a flat rank histogram, so it has rank uniformity. We went through some other variables too, but for the spread skill relationship for pressure is shown right here. So what we wanted to see is that the spread and the RMSE and spread are very similar, and that the RMSE doesn't surpass 1, so the pressure did perform a lot better than what we saw for the fluxes down here.
One more question.
Yeah.
Hi. So, correct me if I'm wrong. It seems like sea or air-sea interactions are more impactful on like a seasonal or sub-seasonal time scale in terms of like predicting changes, but the ECMWF is more of a like synoptic time scale prediction model in general. So, is there a particular reason you use that model as opposed to more of a like seasonal climate model?
Yeah, so for this one, it was one that a past student has actually tried to use in a previous project, so I wanted to like wrap up that project that he was working on. He actually did not use the fluxes, but something that possibly connects to in terms of like the scale of the fluxes. We know that a lot of these are really rapidly occurring, especially in the summer when we were using observations from the summer. I was also trying to use data from 2017 and 2018, so it's possible that different seasonality could affect those as well. But in the future, we would want to work to expand this to include data from other ensembles, such as like the CFSV2 and the GFS model.
All right, thank you so much, Isabella. Next, we'd like to welcome Caitlin King from the University of Michigan. Michigan, not Michigan, Michigan. Welcome, Caitlin.
Thank you so much. Good morning, everyone. I'm excited to talk to you more about biologically inspired design. We already heard a little bit about how birds can inspire aircraft, but I want to bring us back down to Earth and talk about terrestrial legged robots. Why legged robots? To quote my professor, because cockroaches don't need wheels. The insight here is that instead of trying to reinvent what nature has already elegantly solved and maybe complicating it in the process, we can simply look to nature's solutions. So we have what's complex, turn to what's natural, and we get simplified human technologies. So to provide an example of how we can apply this, we look at the challenge of self-righting in decimeter scale legged robots. These robots are uniquely proportioned such that they're small relative to the obstacles they encounter, but they're large relative to their legs. So like you see here, this little guy gets stuck on its back. Currently, mechanisms of confronting this challenge involve active mechanisms, which require things like controllers to coordinate motors and sensors and lots of complicated stuff. But we can simplify this if we rely on passive mechanisms such as body shape. Of course, nature has examples of this, such as tortoiseshells. So this is our little guy, the medium ant robot, developed by a PhD student from my lab. And my project was to design a shell for this guy that would allow it to passively self-right and hopefully be easily manufacturable. We started off with solving this in 2 dimensions. As you can see, this resembles the domed shape of a tortoiseshell. We assumed the location of the center of mass at the center of this circle. And then we also assumed that for these edges over here, the line of action of the normal force when the shell is bouncing on that face acts through the center of the face. Therefore, we have a set of lever arms that allow, when the robot is bouncing on any of those above faces, to exert a restoring torque. Moving into the 3-dimensional geometry, you can see this applied in the green plates in the center module. We also added pointed front and rear modules to help deflect the robot around obstacles. To provide scale, this is about 2 feet long, 1 foot high, and 1 foot wide. So to test this design, we came up with all of the sets of 3 or 4 corners that form a face that the robot could balance and potentially get stuck on, and that creates this convex hole you see here. So we started with this bottom face, and we balance it, and we see the robot return to its upright orientation. Again, moving up the side of the robot, we see similar success. The top face performs similarly. And then we tested faces on the front of the robot, as well as the rear of the robot. Next, we intentionally drove the robot off of a cliff, starting with different heading angles. And we wanted to see, can it survive the impact forces? And also, the fall causes it to tumble, so it will land in a random orientation. So we see here in our coordinate system, we're starting with -60 degrees of heading. And the robot survives, and it's programmed to get up and continue walking after that. More head-on is a little bit more dangerous, still doing pretty well. Getting up, surviving. And then straight on is pretty much a death sentence for this front structure here, but it's successful and gets up. Moving away, we also see the opposite side performing similarly. The robot is symmetric, so we would expect it to perform similarly. And again, for kicks, fun to watch this. So, of course, the robot isn't only going to be falling or navigating level terrain, so future enhancements we might want to make would be improving the strength-to-weight ratio, tweaking it to work on uneven terrain, or to reduce its probability of snagging on obstacles. However, we have addressed the most common type of self-righting we would need to navigate level, man-made controlled environments, and we've exemplified how biologically inspired design can simplify a technically challenging problem. With that, I would like to acknowledge my collaborators, my professor Shai Revzin, also Hal Liu, who originally designed the Medium Ant robot, as well as all of the funding that made this possible, and of course the Astronaut Scholarship Foundation for bringing all of us together and allowing me to share this work with you.
Thank you, Caitlin. We have a question. I have many questions.
Awesome presentation. How do you think this would react in like a sand environment or soft ground that would yield a little bit?
Yes. So this is all manufactured out of foam core. So something I'm interested in is like if there's moisture in that environment. I don't think the paper would take that well, but I'm really not sure how the yielding would affect it. We did calculate that in a worst case scenario, if the ground is tilted about like 16 degrees, the robot still can self-right, worst case. So up to that, we might be okay.
One more question.
Hi, great presentation. I have a question on the material choices that you made. So why specifically those materials, and if you could change anything on the materials, what would it be, and what do you think the test would be like?
So the original design for the Medium Ant was to be an educational robot. So there is like an open source website where you can build your own. And so we're trying to promote outreach with that. And this shell is designed to kind of further that project. So the foam core is obviously cheap. It's easy to laser cut. And so that's the motivation for those materials. Obviously, if we wanted, you could change that depending on what your costs and like environmental constraints are.
Thank you.
Thank you, Caitlin. Now we'll all be thinking about cockroaches driving off cliffs. And on that note, welcome to Brady Moore from the University of Illinois. Welcome, Brady.
Hello, everyone. My name is Brady Moore, and I'm from the University of Illinois. And today I'm going to be talking about some work I did this summer at General Fusion, and more generally just about fusion energy as a whole. So before I begin, I want to talk a little bit about what is fusion energy. Basically, what it is you take light particles, you heat them up a bunch. When they react with each other, they fuse to create a larger particle, and that releases a lot of energy. So some advantages here for an energy source is it's carbon-free, which is great for climate change. There's some inherent safety risks aren't there that you might see in something like a fission reactor. The power output can be easily controlled and match like power cycles during the day. It doesn't have to constantly be running. And there's an abundant fuel, which, as I'll present later, can come directly from the ocean. Some challenges are you have to confine a plasma as hot as the sun, actually hotter than the surface of the sun, and that means materials withstanding heat fluxes that are extremely high, like 10 megawatts per meter squared. And then there's some other issues in plasma stability, and finally economics. It's a very new technology. It's still quite expensive, but as we continue developing it, it should become cheaper. So now I'm going to talk a little bit about how we turn water into this efficient carbon-free energy. So we take water, and from that water, we can extract lithium-6 and deuterium. And what we really want for the fusion reaction is deuterium and tritium. So that lithium-6 gets turned into tritium. Oh, this slide is going to be a mess with all those little letters. I'm sorry about that. But basically, we take the lithium-6. We use a neutron, which we're going to get later. Well, I'll show you where that comes from, to get tritium and deuterium. And the tritium and deuterium gets heated up, reacts into fusion, and that produces that 17.6 MeV of energy, which is in the form of kinetic energy, which is basically heat, and we can use that with a Rankine cycle to spin a turbine and make electricity. And that neutron at the end goes back around to the other side of the screen and is used for the next tritium breeding reaction, so it's a self-contained process. And a fun fact from some calculations I did is that it only takes about 20 gallons of salt water to power the average American house for a day when you extract the deuterium and lithium from that. And that's not a lot compared to even how much you'd use in like a few showers or like washing your dishes. So next, I want to talk a little bit about General Fusion, the company I worked for, and their approach to magnetized target fusion. And that's basically you do a mechanical compression around a plasma target. And so the first step is we have a spinning lithium vortex that basically spinning lithium on the walls. And then there's pneumatic cylinders that are used to rapidly compress that vortex. And right at the last second, there's an injection of something called a tokamak, which is basically a magnetic configuration that contains plasma, so it doesn't have to like touch the walls and cool down. And it continues compressing, and it reaches 100 million degrees Kelvin, so extremely hot, like those temperatures I was talking about earlier. That's why we use that liquid lithium wall there. And fusion happens, it releases a large amount of energy, and that energy is collected in the lithium, and that lithium can exchange heat through like some heat exchange system into a Rankine cycle to produce electricity. And then tritium is filtered out of that lithium, as you saw earlier, that lithium-6 reaction with a neutron to create tritium, which is the fuel. And then it repeats about 1 time a second is their goal. So yeah, you can watch the video all the way through. So now a little bit about what I specifically did this summer. So on the right, you can see a lithium ring, and it's being compressed by electromagnetic forces. So instead of going straight to that big fusion power plant design, the company's like, hey, we need to test and see if compressing things on the order of a millisecond is going to work, and will we actually achieve the compression we need for the plasma. So to start, we just need to compress lithium. So basically, I created those little magnetic sensors you can see on that fiberglass scaffolding. They're small Murnov probes that measure the magnetic field, and then some other Rogowski coils used to measure currents. And the data was used to validate simulation techniques, including COMSOL and LS-DYNA. So on the bottom left here, you can see the dashed dot lines were from a COMSOL simulation of probes at different locations, and the solid lines were the experimental values measured from my probes. And you can see a pretty good agreement for the first half of a millisecond. And then after that, it diverges a little bit, but there's a lot of factors in the simulation that still need to be determined, and the simulation was actually compressing much faster than the real ring. So this data will be important in creating better simulations for the future to design a larger machine. And so some conclusions, I just want to talk a little bit about fusion energy in general. It's been accelerating at a rapid pace. It actually has outpaced the semiconductor improvement, which we all know from like Moore's law is crazy fast for a long time. Recently, it slowed down a little bit as we were getting to ITER, which is this huge tokamak that's going to be coming in southern France, but definitely still on the rise. And this graph shows the triple product, which is a good measurement of basically how much fusion you can produce in a specific device. In addition, there's a growing investment in the private field and public investment. So 2021 was a big outlier there for a lot of money, but also in 2022, it's still growing on a good trend. And then finally, General Fusion is one of the leaders in the private sector, and I think it's a good example of how the private sector is going to be what's pushing forward fusion in the coming years. There's over like 40 fusion companies that have been founded in the past 20 years. And I'm expecting that one of them is going to figure it out pretty soon. So thank you, everyone, for listening to my talk, and I will now take questions.
Thank you, Brady. Let's keep to one question, please.
Great presentation. Do you know what caused the outlier in 2021 with the big jump in funding?
I forget the name of the company, but one of them out in Seattle got like $2 billion from one of those rich people. I forget who, Jeff Bezos or Elon Musk, one of them.
Thank you.
One of those rich people. Okay. 2 billion, 2 million.
Yeah.
Hey. Thank you so much, Brady. Very interesting. Next, we'd like to welcome Sarah Stamer from the University of Arizona. Welcome, Sarah.
Okay, mic check in the back. Am I good?
Okay, cool. I see thumbs up. That means I'm good. Perfect. Good morning, everyone. My name is Sarah Stamer. I am a rising senior in astronomy and physics at the University of Arizona. But for the next couple minutes, consider me your science superhero because I'm going to be talking about the research I do to combat fake science online. So, quick show of hands. How many of you think science is useful? Okay, everybody's hand is up. Super cool. How many of you read about science online? Okay, I see everybody's hand again. How many of you think if I gave you a series of questions about science, you could answer 2/3 correctly? 2/3? Okay, little less. But, okay, anybody out there ever fallen victim to science misinformation? See a few people read something too good to be true? So, my project is for you. My project is for all of you, but especially you all. We are developing a neural network, or AI, to detect science misinformation in online articles. So in order to do that, we need articles. So we use a link website right about here. We have 10 different pseudoscience topics where we were looking for articles that were real and articles that were fake. Our initial goal was about 100 real, 100 fake for each topic. That's 1,000. That's kind of a lot, but we were getting close. But then comes my personal favorite part. This right here is what we call Science Tinder. It works like normal Tinder, I promise you. But what you can do is you swipe right if it's a real article and you swipe left if it's a fake article. We just use that as kind of a check mechanism to make sure that we were all on the same page with how an article was being classified before we sent it to the neural network and said, hey, we have to make sure our classifications agree first before you start classifying things. But the next phase, of course, is very important because in science, you may have heard that extraordinary claims require extraordinary evidence. I think that in good science, we just need some good claims and some good evidence. So we were able to look at some of our articles, real science, fake science, and look for claims and evidence. If you had a claim but no evidence, probably an indicator that something was fake, or if you had evidence that's just not real, then that would put you probably on a fake science path. But the newest phase that we've been working on is using ChatGPT and data sets. I'll get to ChatGPT in a second. I know everybody's eyes just like perked up about ChatGPT. Don't worry, I'm getting there. But selecting articles one by one is pretty tedious. It takes a giant team of undergraduates multiple years to try and select these articles. And we need a lot to train this AI. And it's not easy to do it, but recently we decided to run into data sets of articles. Some of my personal favorites, UFO sightings. We had data sets of like 20,000 UFO sightings, locations, times, what people saw, how long, and all of that stuff. Another personal favorite, flat earth conspiracy tweets. There's a lot of those, which is kind of surprising to me, but you know, it's always good to have kind of a mix of real and fake science to include there. And then of course, ChatGPT, you know it, some of you love it so much, but it is great to use AI to write examples for us. Makes our job a lot easier. So we would have it write mock stories about, you know, UFOs coming in and taking over Earth, or UFOs just being a plane. Blog posts, tweets, writing assignments, we were able to kind of come up with different prompts to use in ChatGPT to kind of make that shift. And using our data sets and these older articles that we found before we started working with data sets, our reliability was up to 90%, which is pretty impressive because we haven't really been able to do anything like this before. So we are very proud of that number. In the future, we plan to use this to launch in general education courses, especially in the astronomy department where I work, for students writing about science in their courses. We want to make sure their claims and evidence are good. We have a Rotten Tomatoes scale that we want to bring out where you have very fake science and very legitimate science, and why, that we hope to launch into browsers and your own version of Science Tinder. So take a look for that. And this is very important because if you remember your responses to the opening questions, you know why we're here. Fake science is easy to create, and this is a very critical issue that has only increased. If you have been around the pandemic, you know how much science misinformation came out. and it's only going to increase at this point. I would like to thank my advisors, Dr. Chris and B, Dr. Matthew Winger, and the Active Galactic team, all my amassed funding sources, and of course the Astronaut Scholarship Foundation for this opportunity. Thank you, and I will take questions now.
Thank you, Sarah. Quick question.
Hi, that was a very interesting presentation. My question is, can this method be applied to more scientific papers, like technical papers, and to see if they're actually legit or they have some claims that they're not really backing up?
Yeah, so we were mainly focused on like the online science article part. So our whole goal was, once we were selecting articles, we said like no journal articles. We were like, we're not even gonna touch that. So eventually we hoped that maybe it could make an impact there, but we hadn't really had the time to test it. We've just been working on something that's kind of more applicable to the general public rather than just like the scientific community.
Okay, thank you.
One more quick question.
So the way you're training the data set is to have humans like swipe right or left, right?
Yeah, so that's our initial like classification.
How do you make sure that the humans that are inputting the training data are reliable?
So it's kind of hard. There's a lot of undergraduates who have worked on this project over many years, and we all have different science backgrounds, and so a lot of us are in astronomy, but not everybody knows about like climate data, for example. So we try and get, our reliability is honestly pretty good. It's also around 90%. It might be a little lower than that, but we try and stick with articles that we can all relatively agree on, no matter kind of where our science backgrounds are landing.
Thank you, Sarah. I don't know about you. Now we got cockroaches on wheels and galactic tinder. That's funny. Do I have to tell you that's funny? Oy, oy, oy. All right, next, let's welcome Christy Barnes, North Carolina A&T State University. Welcome, Christy.
Good morning, everyone. My name is Christy Barnes. I am a senior honors chemical engineering student with a minor in applied mathematics at the illustrious North Carolina Agricultural and Technical State University, which is the #1 public HBCU, the largest historically black college and university, and the top producer of black engineers in the country. So today I'll be presenting a research paper that I assisted a biology professor at North Carolina A&T in writing. It is the study on the effectiveness and adherence to mask mandates in stores in Greensboro, North Carolina. Moving into the background, as we all know, we experienced the COVID-19 pandemic, which is a disease caused by the SARS-CoV-2 virus. During the pandemic, we were recommended to social distance, to wash our hands frequently with soap and water, and most importantly, to wear masks. Why we were told to wear masks? They prevent wearers from spreading particles to others, and if it is properly fitted, it will also prevent them from contracting the virus from people that are contaminated with the virus. During the pandemic, the United States had no federal mask mandate, so this was ultimately left up to the states. And in the state of North Carolina, in summer 2020, the governor issued an executive order for the mask mandates, and the Greensboro mayor established an emergency proclamation to reinforce this executive order. So this study was a local direct observational study done in Greensboro, North Carolina during the summer 2020 COVID surge, where there was an increased number of hospitalizations. The reason why we chose Greensboro, North Carolina, this is where North Carolina A&T is located. It's also the 3rd largest city in North Carolina and the 66th largest city in the United States. So our objective was to determine if Greensboro shoppers adhere to mask mandate signs in local stores. Store owners could also be fined $100 per person that was found without wearing a mask in this time. And our hypothesis was that not all shoppers would adhere to the face mask mandates. And we've structured it in this way because in this time we still didn't have the vaccine, so we just didn't know a lot about the virus during this time. So how we went about executing this research We visited 5 different types of stores. This included convenience stores, pharmacies, grocery stores, gas stations, and clothing stores. And these are 5 essential stores that most people will visit on a daily basis at some point. And we visited in the 3 most frequently visited times: morning, afternoon, and evening. So we noted the 10 male presenting and 10 female presenting persons every second, male or female, that entered the store. And all of the stores that we visited had a mask required for entry sign, and then we calculated the percent of people without a face mask. So from the data we collected, we found that more men than female were found without wearing a face mask. In the morning, there was on average a significantly high number of males seen without face masks in convenience stores and pharmacies compared to females. So males, it was 51.1%, and females 15.1%. In comparison, the number of males and females seen without masks were similar but much lower in the grocery stores and clothing stores, and there was a significantly higher percentage of female shoppers, being 50.1%, than male shoppers, being 10%, seen without face masks in gas stations. Moving into the afternoon data, there was again, significantly higher number of males shoppers seen without face masks in convenience, grocery stores, gas stations, and clothing stores. And moving on to the evening data, there was a significantly higher number of males, being 53.3%, than female shoppers, being 27.6%, seen without face masks in grocery stores, pharmacies, and gas stations. And in clothing stores, there was a significantly higher number of females seen without masks. So our hypothesis for this study was true, that not all shoppers adhered to the mask mandates. There was the highest percentage of people not wearing masks in the afternoon compared to morning and highest percentage in the evening compared to the morning and afternoon. And there was a significantly higher percentage of males seen without face masks in comparison to females. And this has been seen in previous health issues like influenza. Just men are a little bit more risky sometimes day to day. So they were more susceptible to contracting COVID. And future directions for this study, this was largely a human factors study, so we're obviously not robots. We have our own free will, we make our own decisions, so this leads to issues with human factors, and there's a lot of different variables in this study. So moving into future research, I'm interested in working in the healthcare and pharmaceutical industries, and human factors plays a large application in regards to medicine and for different products that are created to help improve people's lives day to day. So I'd like to acknowledge my PI, Dr. Akamajud Abunkem, as well as my parents and my aunt and cousins that came to support me today in the back, and the North Carolina A&T ASF liaison, Ms. Alsace Gallup, as well as the Astronaut Scholarship Foundation for this opportunity to come and present to you all today.
Thank you, Christy. Questions?
I had a question. If you've looked, and if you did, was there a correlation with local cases that there are more male cases than female cases, since it seemed that men tended to not wear the masks as often?
Yes, we did find that correlation. There were more men hospitalized due to contracting COVID in this study. So it did correlate. More men were not wearing masks, and more men did end up hospitalized from the back.
One more question.
Very nice presentation. I was just wondering if you took a look at different types of masks and whether that had any effect between the male and female population.
Yeah, so in this study, we did not look at different types of masks, but in the research paper, if you'd like to scan, we did reference other, we have our references in there, and it was noted that a properly fitted mask would protect you more from contracting the virus as opposed to like a cloth mask that people often had to use during that time.
Thank you so much. What a topical, interesting presentation. Thank you, Christy. All right, our next presenter to welcome is Hannah Woodkey from Miami University, Ohio. Welcome, Hannah.
Hello. My name is Hannah, and today I'm going to be talking to you about the electron microscopy and bulk chemical investigation that myself and my co-authors carried out on a bottle of talc-based baby powder manufactured by Johnson & Johnson in 1985, and what this tells us about the product's contamination and also the insights into its sourcing. I'd like to take a minute to acknowledge everyone that's contributed to this project. So my immediate mentors at Miami, Dr. Mark Kreckler and Dr. Claire McLeod, as well as Dr. Ken Brown at DePaul University, and graduate students Morgan Gillis, Kaylee Goki, and Madeline Merchland. So before we talk about the baby powder, we should set a little bit of geologic background with talc. So talc is a hydrous phyllosilicate mineral that occurs in marbles and altered or metamorphosed mafic and ultramafic rocks, which are otherwise known as ophiolites. We're going to talk about those a bit later. It's a classic 2-to-1 layer phyllosilicate that's held together by weak hydrogen bonding, and I've listed its ideal chemical formula there and listed a picture of its chemical structure on the top right, modified from Dumas et al. It's worth noting that in the octahedral site where the magnesium is, iron, nickel, and chromium are able to substitute into that structure. And because it's really soft, it has that soft, slippery feel that we all know. It's actually the softest mineral. It's had a whole variety of historical and current uses. I've listed them all there, but we're mostly going to talk about baby powder. This may have sort of jogged your memories. It's been in the media recently. So it sort of came out that Johnson & Johnson was aware that asbestos was in its baby powder products, which is extremely concerning for a number of reasons. Asbestos is heavily correlated with mesothelioma and ovarian cancer, and it's pretty well recognized that that's an issue in both the mainstream media and the scientific literature, but we wanted to know what other contaminants could potentially be in there, depending on the geologic sourcing. It's also worth noting that when you use baby powder, it's suspended in the air. So any tiny particles around less than 10 micrometers in diameter are things that could potentially enter your body. This is our sample. It came from a whole suite of samples we had spanning back from the 1960s to present. And you'll note in image C that the only ingredients are talc and fragrance. We mostly focused on using transmission electron microscopy. This is our Joule 2100 microscope in the Center for Advanced Microscopy and Imaging at Miami University. Although we're able to collect all these types of data, and it was really interesting to see chemical mapping provided by some of the scholars yesterday, we're mostly going to talk about chemical composition and particle size to identify the particles and also understand how they could be introduced to different systems in our body. We also have some examples of polarizing light microscopy and scanning electron microscopy. SEM is a great tool to use because we're able to use the energy dispersive spectroscopy, which gives us that chemical composition, same as in the TEM, and we're able to use backscatter detection, and when you insert that detector, anything that's elementally heavier will appear very bright. So if we're looking for things like metals, they'll just pop right up and they're really easy to identify. I have a ton of TEM and SEM results, but I don't have time to get into all of them, so I picked a couple representative images. So in the specters on the bottom for both of these images, you can see magnesium, silicon, and oxygen. These are our elements in talc. This is what we would expect. And also because it's TEM, we have copper that's coming from the grid that we mount the sample on, so completely expected. We also find that this talc has iron and nickel, and we interpret this as being inherent to the talc and to the source. On the left there, we have a talc fiber. Fibers are normally defined when the C-axis is 3 times longer than the A and B axes. And it's actually worth noting that in 2021, these became able to be counted as asbestos particles. And one area of future research, it's been noted that iron can be associated with enhanced toxicity. And on the right there, we have just a standard example of a platy talc particle. Some sample SEM, so we can see on the top that particle's a bit brighter. That's the backscatter that I mentioned. This is chromite. You can sort of see maybe laser. It's sort of, you can tell that the axes are about equal lengths. And the chromium and the iron in the spectra was what clued us into this. It's very small. It's less than 1 micrometer in diameter, so definitely able to enter your body. And on the bottom there, we have this elongate fiber. However, it looks anthropogenic. It's a carbonate. It has zinc on the spectra. This is not asbestos, this is not a talc fiber. We interpret that this could actually be glass, and I have zero insight into the manufacturing of this product. All I know is that this ended up in the bottle that we used. So in order to put those results into context, we used XRF to do bulk chemistry, and the big takeaway from this is that we have over 2,000 parts per million of nickel and 500 parts per million of chromium. We're gonna have to do a lot more work to understand how that's actually presenting in the sample, the phases, the minerals. But what we do know is with those metals, there are certain amounts of health effects. So nickel, some of you may be aware, you can develop allergies to nickel. People who have worked in mines, it's a lung irritant, can enhance asthma. And chromium, it really depends on the valence state. I'm sure we probably know about hexavalent chromium, things like that. That's stuff that I don't really have much insight to right now. But those metals could clue us into the sourcing. So around the same time frame, it was pretty well documented by this paper, Chidester 1962, that rocks in Ludlow, Vermont had an elevated chromium and nickel content, and they're those ophiolite deposits that I talked about earlier. And that's a major manufacturer of talc. Based on context, we could assume that Johnson & Johnson could have possibly mined talc from this location and used it in their products, but we also don't know about potential like mixing from multiple sources, but this is a pretty likely place. So we were actually able to obtain ore that was collected in the 1990s and do a similar analysis. So this is that polarizing light microscopy image I talked to you about earlier, and this is in polarized light, cross-polarized light. And all the material that sort of looks like a swimming pool, I guess, is talc. And then the dark spots are unidentified oxides and sulfides. So this could potentially be the chromite that we talked about earlier. It could be pyrite. We also saw some of that. So we know that it's also there. We have many facets of data that are telling us the same thing. And we also did another bulk chemical analysis, and we found that chromium and nickel are also elevated. So there are a couple of reasons why those numbers are pretty different. We, like I said, don't have much insight into what happens in the manufacturing. So mineral refinement during processing could have altered those compositions. Also, statistics, we only have one bottle, and mines are huge. So the chemical variation there, the numbers could be pretty different. So it's actually pretty incredible that they're similar in this analysis. And also, of course, the baby powder could have always been derived from another mine. But this definitely opens the door for more analysis in this time frame and in also other time frames, looking for things that are associated with these types of deposits, doing more work into asbestos, and that's all I have. So I'd like to open the floor for questions.
Thank you, Hannah. Where's our first question?
Hi, really interesting talk, thank you. Are you guys planning to try and reach out to Johnson & Johnson to try and correlate some of these findings? Not that they'd probably be super happy about hearing about this.
So Johnson & Johnson actually recently, I think, reached an $8 billion settlement. It's been not so great for them. And right now, actually, all baby powder on the shelves made by Johnson & Johnson in the US is cornstarch-based. So they do not make talc-based baby powder anymore. There are still other talc products on the shelves, like cosmetics, makeup. But yeah, no.
One more question.
Did you look at any possible organic contaminants also, or just inorganic?
Not really. I don't think we found any. We did a lot of TEM and SEM, and I don't think we found it. We might have found a couple different carbon fragments that could have been who knows what, skin or something like that, but not really.
Thank you very much, Hannah. Our next presenter to welcome is Madison Brody from Mississippi State University. Welcome, Madison.
Hi everyone, my name is Madison and I'm a rising senior at Mississippi State studying biology. And for the past few years, I've been working on songbird breeding behavior with the University of Memphis. So I'll be telling you guys about a study looking at parental favoritism in a wild bird population. But before I get into that, just imagine for a second that you have like 6 young, needy, annoying children all begging you for food, but you can only feed one of them. That's basically what breeding songbirds worldwide do every single year. So many songbirds raise more than 1 young at a time. Some of them even raise up to 12 or 13 babies. However, they're usually only capable of bringing 1 or 2 food items to the nest at a time. And as you can see, they can be very big beggars. And so parents have to decide which child or baby to feed. The purpose of our study was to look on if they have certain strategies that they use to feed their children, and if so, what are these strategies? So we have 2 hypotheses that we were specifically looking at. The first one was, do they feed the smaller, needier young preferentially, or do they feed the larger, higher quality young that are least likely to be a wasted investment? So to do this, we went out into the forest at Meeman Biological Field Station, which has around 600 acres of land, and we set out nest boxes across the land, which you can see in that white photo right there is a map of it. And these nest boxes attract this bird, specifically known as the prothonotary warbler, and they're the really cute small yellow bird, as you see pictured there, and they will nest in nest boxes and have 4 or 6 young at a time. And what we did is we basically took videos from inside the nest to see what the parents were doing. And as you can see right there, there's 2 little babies begging, and the way we identify them is using whiteout. And what we found is that nestlings that begged more tended to be fed more food overall, which makes a lot of sense, but also that smaller nestlings begged more frequently than their larger nestlings. But this did not necessarily mean that they were fed preferentially. In fact, that seemed to be mostly influenced by clutch size. So small broods where there were just like 3 individuals tended to have parents that preferentially fed larger individuals, whereas in large broods, parents tended to preferentially feed smaller individuals. In other words, larger, higher quality young tended to be preferentially fed in smaller broods, whereas in larger broods where there were more children, parents tended to feed the smaller, needier young. But overall, smaller nestlings still tended to beg and gain more weight across the entire observational period. My clicker is not working. But anyway, so why this might be happening? So this was just an observational study, and future work focused on manipulating brood size could potentially show like causation rather than just correlation, but some potential reasons why this might be happening is again, so larger nestlings are more likely to survive and reach adulthood and may have better overall long-term success, and therefore might be a better way to go about producing future generations, whereas in larger broods, when you have the opportunity to produce a large quantity of young, that might be another strategy for trying to produce as many future generations as possible. So there might be multiple strategies for producing young. But overall, it does look like they do have some methods that they use, but what exactly they are and why they do it still needs to be better investigated. But anyway, I'd also like to thank the Bowers Lab at the University of Memphis for helping me with this research, because they were great and they were out in the forest collecting data in 100-degree weather for this. So yeah, that was great. But I am open to any questions if anybody has any.
Thank you very much. Question number 1.
I didn't think I would listen to a presentation on bird child neglect today. I was wondering how many members of the brood would be required for the birds to switch over from feeding the larger ones to the smaller ones?
Yeah, so that's actually something that we're currently investigating by manipulating brood size specifically. But But as you could see, like when it was just around like an average number of broods, it didn't really seem to make a huge difference what this strategy was for them. It seemed more like on the extreme ends of clutch size that you seem to see that variation.
One more question.
Hi, thanks for a great presentation. I don't know if the species or if songbirds in general experience brood parasitism, but is that a factor that you guys are planning to look into in the future in terms of differential feeding?
Yes, actually, so these birds are commonly parasitized by that bird right there, which is called the brown-headed cowbird, and they parasitize a lot of songbird species, not just prothonotarians, but what we've received, especially in the last couple of years, is we have had frequent brood parasitism. And what this does is it not only makes another bird in the entire nest that is a very, very energy, like a big energy sink because it does grow so quickly, but they also tend to eject eggs from the nest, while they're laying their own eggs there, and that can also change clutch size. So. Yeah.
Okay. Thank you very much. All right, let's welcome Brianna Robinson from North Carolina A&T State University. And let's make sure the clicker works. Yay.
It does work. Okay. Let me do this. Hello, everybody. I'm so sorry to do this to you before lunch, but I want you guys to imagine a big, juicy burger. Tomatoes, lettuce, bacon, mustard. I don't like mustard. Ketchup. Imagine that. Yeah, that's not what my project's about, but I just wanted to get your attention because, you know, everybody's showing off. But my project is about the actual animals that go into making that beef for you. So I'm looking at the effects of direct-fed microbial treatments on reducing incidences of ruminal acidosis. So a little bit of background for you guys. We all know that the human population is growing and growing and growing. And producers have to keep up with this by producing more food. Beef is one of the most highly consumed foods across the world. A way that producers used to keep up with this is being able to use antibiotics and growth hormones. Well, we saw how that went when it got banned in 2017. So what they do now is they have increased the amounts of dietary carbohydrates that they give to their animals. But this is detrimental. This causes acidosis. So I don't know if you guys remember this, but there was this Drake and Josh episode where they were packaging up these, they were working in like a conveyor system, and they were packaging these like little cartons and stuff. So at the very beginning, you know, it was going smooth. They were coming through slowly. They were able to keep up. But as time went on, there was more cartons and more cartons and more cartons, and they couldn't keep up at all. This is what happens when you feed these increased dietary carbohydrates to these animals. It causes a buildup in lactic acid, and the rumen is not able to support this. The rumen, which you can see, which you can see right here, it's one of the compartments of the cow's stomach. And this negatively affects animal health and production. So, why use direct-fed microbials? So direct-fed microbials are live microorganisms that are naturally existing. So this means that we wouldn't be adding anything that's not already occurring within the cattle's body or that's already naturally occurring that we eat already. So this can also potentially mitigate ruminal acidosis once it has occurred. So our hypothesis for this entire project, what I'm about to present on, is the first step in a long journey that we have, is that the utilization of direct-fed microbials and plant nutraceuticals will be able to increase the pH and mitigate the effects of ruminal acidosis. So how do we do this? Basically, we made a rumen outside of cattle. I know, it sounds crazy, but it's possible. So we took these tiny batch culture bottles and we put two different types of feed, pellet feed and then pellet and starch. Pellet and starch was used to kind of exemplify what it would be like to have the excessive dietary carbohydrates. And then we added certain treatments on top. So the treatments that you see here, C1, C2, and C3, these are all commercial direct-fed microbials. OP is onion peels, MOS is mannan oligosaccharides, GOS is galacto-oligosaccharides, and then a combination of both the onion peels and the oligosaccharides, and then an essential oil blend. So, how do we do this? We put each of these feeds into these tiny bottles and then added each treatment on top. Then we took an artificial saliva solution and added those to each bottle. And this is the interesting part. I don't know if I have enough time to go through this whole thing, but basically we took the microbes from the actual rumen of the cattle. And we did this to test gas production, which was done at 6 and 12 hours. So what were our results? So what we saw that we were able to induce acidosis in these tiny bottles. As you can see on this graph, you can see that the pellet pH was a lot higher than the pellet and starch. And they were both kind of at an acidic level, but you can see that the pellet and starch was at a much lower level, which is what we wanted to see because we wanted to prove that we can induce acidosis. So what you see on this graph here, which was really interesting, is that the essential oil blend was actually higher than the control. So that's something that we will be looking into the future. And you can also see on this graph right here that the pellet was higher than the pellet and starch, the pH. So what are some conclusions that we made from this study? We saw that the addition of these additives reduced the digestibility of the acid detergent fibers and the neutral detergent fibers. We saw that the pH of the pellet feed and the pellet and starch feed, that the pellet feed was a lot higher than the pH the pellet and starch feed, sorry. The mannan oligosaccharide had the highest gas production for pellet and starch, and that C3 had the highest methane production for both, and that C1 generated the highest ammonia and hydrogen sulfide. We will be continuing to study throughout the next 2 years on ways that we can combine these treatments in order to provide mitigation of ruminal acidosis. These are my references, and I just want to thank the Ruminal Nutrition Lab at North Carolina A&T, my advisor and principal investigator, Dr. Uchenna Anelli, Dr. Peter Dele, and Dr. Adaluski for helping me put together these slides, the Astronaut Scholarship Foundation for letting me present, and the Undergraduate Research Scholars Program for funding my research.
Thank you, Brianna.
I'll take questions, yeah.
Let's have a question.
Great presentation. How did you ensure that your sample of human gut, or not human gut, cow gut microbes was representative of the rumen as a whole?
Okay, so this might gross some people out, but just stay with me. Basically, we had cannulated cattle, and how that works is, so you have a cow, right? And you basically draw a circle on its body. So I'm gonna use my own body for reference. So act like this is my stomach. We're drawing a circle around my stomach. We take this part of skin out, we cut through the fascia, we reach in, grab the rumen, pull it up, attach it to the outsides, cut it open, sew the outsides together, and then you know how like in a bathtub you have a stopper? We add the rubber outside and then put a plug on it. So when we're actually gathering like those samples, they're actually like my arm is inside the cow. Yeah. I had a picture, but I didn't want to gross people out before lunch and stuff, so yeah.
I'll just say, yum. Next question. One more.
You mentioned something that happened in 2017.
Yes, so the use of antibiotics and growth hormones were banned use in animals because they had adverse effects on our population. They were using it to increase the average daily weight gain. So they were using it to basically make the animals bigger in a shorter amount of time to increase production. Yeah.
Okay, again, I wonder where the growth hormones haven't stopped for humans quite yet, but it could be the pasta that we eat. Brianna, thank you very much. Very interesting. So we want to thank Garrett Knotts from Mississippi State University to come up now because he is our last presenter. Not an easy place to be, so let's clap him in. Hi, Garrett.
And since I am last, I will take as long as I want. No. I was told not to do that. Okay. Hi, guys. Oh, let me go ahead and change the slide. My name is Garrett Knotts. I am a senior biochemistry student at Mississippi State University. And what I want to convince you of today is that your heart is extremely important. It's an important muscle organ. And one thing that's really interesting about the heart is that the cells that make up your heart aren't like other cells. They don't divide. So if the cells don't divide, a lot of issues can occur, and that can cause a lot of issues for you. So today I'm going to be talking about a drug called liraglutide. It's better known by its shelf name, Victoza. And so Victoza is a type 2 diabetes medication that is gaining a lot more popularity for its potential as a weight loss medication. And so my talk today will primarily focus on potential negative effects on the heart in an aged population. So let's look at some mice. What we see here are the electrical currents on the surface of a mouse heart when given this drug, liraglutide. What you can see in our adult is that it maintains pretty rhythmic beating, what you would expect in a normal heart, human or mouse. However, once we go to our aged model when given our liraglutide, well, that doesn't look right. We start to lose our rhythmic beating. So naturally, as we get older, you can expect heart health to decline because, our cells don't divide, so you're stuck with as many as you have. The older you get, the less you're going to end up having. So that led us to our first statement, getting old stinks. But our application of liraglutide could potentially make that worse. So we wanted to go from the organ level down to the cellular level and see what's happening. So this electricity is caused by the flow of ions into and out of the cell through proteins called ion channels. And so our AP, designated action potential, you can see that this is measuring our electrical currents on the surface of a cell, of our cardiomyocytes. And you can see kind of well, there's a wider peak in our aged and liraglutide model. This means that our channels aren't functioning properly. The electricity isn't quite right. So we were able to use some pharmacological blocking and narrow it down to our sodium and potassium currents. And so our lab primarily focuses on the sodium channel, otherwise known as NAV. Here is just a lot of data that backs up something's wrong. And so going from sodium, we now must understand that our electricity, the reason we want that is to release our calcium, which causes our muscle to contract. And so what we see here in the green, other than one of these obviously doesn't look like the other, it's our calcium in one of our cells. So the amount of calcium is lit up with a fluorophore. As you can see in our aged and liraglutide model, there is this big old green streak of calcium, which tells us that our ion channels are being mistimed and are mishandling calcium, which is bad for the heart. And we were able to track this back to our sodium channels being open for too long. So then we had to ask the question, what is impairing this? What are causing these issues? So we looked at a couple things that are common in different diseases through all physiology. And we narrowed it down to a potential increase of phosphorylated casein kinase 2. And when we inhibit this casein kinase 2, well, look at there. It fixes itself. So this orange is our age with liraglutide, and we go back to normal when we add the CK2 inhibitor. So awesome. But then we came to an interesting thought. What is CK2 and what is it doing in the heart? Well, casein kinase 2 is super important for cell division. Well, if you remember what I told you earlier, they don't divide. So what is this doing in the heart? Well, through literature review, we figured out not much. We don't know what is going on with CK2 in the heart, but we know that it doesn't directly interact with the sodium channel. And so then the question becomes, what is this? So back in 2019, we looked at another inhibitor called KN93 and noticed that this KN93 bound to another protein that is important for the sodium channel function called calmodulin. And we noticed that it had a similar structure to our casein kinase 2 inhibitor, simvastatin. There's a reason I have not been saying the name, because it's very complicated. So through that, we wanted to see, could this possibly happen that our calmodulin and our CK2 inhibitor might be interacting? So we did some NMR titrations and tracked all the amino acids. And so as the colors change, that designates an interaction. And so next step is going to be to try and get a structure of this through doing X-ray crystallography to better understand from a structural aspect what's going on. And so with that, I would like to thank my lab and Dr. Johnson for allowing me to come and present to y'all. I'd like to thank AESF, and I would like to thank our collaborator from Ankara, Turkey, who also did a lot for this project, Dr. Yusuf Olgar. So thank you.
Thank you, Garrett. There's a question there.
Thanks for the talk. Really exciting results. I'm interested to hear how did you make your aged model? Was it literally aged mice that were just older?
It's just aged mice.
Awesome. Thanks.
And one more question.
Does Victoza have the cardiac arrhythmia as a listed side effect? Or if not, did you contact the pharmaceutical company about that?
I'm not sure. I don't think they do as of yet, but we have not been in talks with the pharmaceutical company about that.
Okay, thank you, Garrett. And I'll just say growing old is not for the faint of heart. Thank you.
Thank you all.
You are all wonderful. You've been here all morning. How exciting was this? These scholars are awesome. So I want to give a couple of notes on thank yous before we close. First of all, thank you to Ashley, my co-moderator. She is very good at keeping me on time. Will you follow me around the world, please? Thank you. So I also want to thank the ASF team. Now you've seen, you know Carolyn, you know others, but there's a whole lot of people that made this possible and made it so fantastic this year. So give a hand to all the ASF team. I want to thank also all of my fellow Board of Trustee members and our fantastic Board of Directors for supporting the Scholarship Foundation and for supporting all of you all day, every day. Thank you to the Board of Trustees and the Board of Directors. To your families, dear scholars, some of you said you were annoying. I didn't find it so, and I would tell you. But thank you to your families for sacrificing everything to make sure that you are here in this present moment. So thank you to your families, your friends, and all of your supporters. So in closing, I'll just say I loved the quote from our Spelman scholar, and I forgot your name, but Winter. I should know that. I live in Minnesota. Winter is coming, Game of Thrones. You all have a choice to, I'm going to say, keep changing the world. Thank you all. What a wonderful event. Thank you.
And can we please thank our moderators? You were very witty, Carol. Thank you. And what an awesome audience. You all had great questions. Thank you so much. This concludes the 2023 Astronaut Scholar Technical Conference. What's next? Time to party, right? All right. So we'll see you all at Gala this evening. Reception starts at 5 o'clock. Scholars, what time do you have to be there? Be all gussied up and ready to go. 4:30 for your walkthrough. Headshots in Turkey Lake after this if you wanted to get those. Since you're all dressed up, might as well take a photo. Thank you all so much. Have a great day.